So namaskar, adab, sat shri akal, kaisa hai, 𝐂𝐤𝐬𝐿, hello and welcome in GATE Wallah. So in this session, what we'll do, we'll discuss the previous year questions of vibration chapter which has come in GATE Aerospace. Okay, so we are going to discuss the PYQs of vibration. Okay, so starting, see, this is first question. What this question is saying, since exam is near na, so we are not delaying. Directly we are coming to the point. Today we are going to discuss PYQ of vibration. So I am starting without any delay. See, one by one. See what this question is saying. This is multiple choice question. Means out of this 4 options, any one option will be correct. It is saying consider a single degree of freedom, a spring mass system of spring stiffness K1 and mass M, which has a natural frequency of 10 radian per second. Now, consider another system, again single degree of freedom system, in which spring stiffness is K2 and mass is M, has a natural frequency 20 radian per second. Then examiner asking what is spring stiffness KT in terms of K1, because options are given in terms of K1. So there are two cases. In case 1, it is a spring mass system in which a spring of stiffness K1 is attached to a mass M. Okay, and for this case, natural frequency is given, suppose that is omega n1 and it is 10 radian per second. Now in case 2, a spring of stiffness K2 is attached with the same mass is again M. Now for this question, omega n2, that is natural frequency, is 20 radian per second. So indirectly we have to find the relation between K2 and K1. Now we know for general spring mass system, the formula to calculate natural frequency is root K by M. Okay, so can I say here omega n1 is nothing but root K1 by M. Okay, similarly can I say omega n2 is nothing but root K2 by M. Now suppose this is equation 1, this is equation 2. So what I am doing here, I am calculating equation 2 divide by equation 1. So we will get omega n2 divide by omega n1. Now it will be equal to, okay, see here now 1 by root m is common in both the equation. So that will get cancelled when you will take the ratio. So can I say omega n2, it will be root k2 by omega n1. So it will be nothing but root k1. Okay. Why I am not writing this root m part? Because it is common in both the equations, so it will get cancelled. Okay. Now omega n2 is 20 radian per second divided by omega n1 is 10, that is equal to root k2 by k1. So root k2 by k1 is coming 20 divided by 10, that is 2. So definitely do the square of both sides, so we'll get k2 by k1, it is coming 4. So k2 is 4 times of k1, and this relation examiner is asking. So here k2 is coming for this question equal to 4 times of k1. Okay, 4 times k1, matching with which option? Option D. So for this question, the correct answer is option D. Okay. Okay, now I am moving to next question. If you have solved any question, you can also post your solution or answer in the text in the chat. Okay. Now this is next question. This is also very good question. What this question is saying? This is multiple choice question which has come in GATE 2007 2-mark question. A 1 kg mass attached to a spring elongates it by 16 mm. Okay, so it is the static deflection of the spring due to this mass. Okay, now mass is then pulled from its equilibrium position by 10 mm and released from rest. Okay, now assuming the acceleration due to gravity is 9.81 meter per second square, the response of the mass in mm is given by, okay, so which equation is correct, that examiner is asking. So see here what this question is saying, a mass of 1 kg when we are attached in the spring, suppose the stiffness of the spring is K, right? It is not given. So due to this mass, static deflection in the spring is 16 mm. Okay, so after attaching this mass and the value of mass is 1 kg, suppose spring coming here, means this is representing the static deflection of the spring due to this mass, that is delta, it is 16 mm. So by using this information, we can calculate the stiffness of the spring. That's why only this information is important. Okay. Now after that, what we are doing? We are displacing this mass from its mean position by 10 mm. Okay. Then releasing this. So it will vibrate this. This vibration will have some equation. So examiner is asking the equation of that vibration. But before that, I am calculating the stiffness of the spring. See, can I say it is the static deflection of the spring due to the weight of this mass. Now, if mass is m, weight will be mg. Okay, weight will be mg. Yes. And due to weight, if static deflection is delta, so can I say here spring force will come, which will be k delta. If you are drawing the body of mass, it will be opposite to delta. So since delta is downward, so it will be upward. And since it is static deflection, okay, so when this deflection is occurring in this system, the system will be reach in equilibrium. So this is equilibrium position. Equilibrium position means at this position net force will be 0 and not force is 0 means can I say here mg is equal to k delta, because mg minus k delta is 0, so mg will be equal to k delta. So through this we can calculate the stiffness of the spring. Here mass is 1 kg, G examiner is saying 9.81 meter per second square. Now I am using SI unit na, so k, so delta, put delta in meter. Delta is 16 mm, so in meter it will be 0.016. If you take SI unit na, chances of unit mistake will reduce. Okay, so from this we can calculate stiffness of the spring. How much it is coming? 1 into 9.81 divided by 0.016. It is coming 613.125 Newton per meter. Yes. So now what I am doing here, I am drawing its mean position, because during vibration na, you have to nothing to do with the how much spring is deflect at mean position. Only what is mean position, that is important. So this is mean position. Now what we are doing, from this mean position, we are disturbing this mass by 10 mm, then releasing from rest. So what we have done, okay, to disturb this mass, I have applied an impulse force and I have disturbed this by 10 mm. Okay. Now at this position, the impulse force which we have applied in this mass, we have released that. So it will vibrate like this. Yes. And examiner asking equation of that vibration. Okay. To calculate equation of that vibration, since here no damper is attached, during vibration no external force is acting, so it is natural vibration. So first calculate the natural frequency of this vibration. And for a spring mass system, what is the formula to calculate natural frequency? Now it is root k by m. Root k by m. Now here root k by m. K we have already calculated. It is 613.125 divided by the value of point mass m. It is 1 kg. So from this I can calculate natural frequency. It is coming root over 613.25 divided by 1. Is it coming 24.76 radian per second? See, this is natural frequency. Okay. Yes. Now when you have calculated natural frequency now, so whenever this mass is vibrating, so suppose during vibration, its displacement from mean position is x. So we have to find the equation of vibration, means we have to write the equation of x. And we know in natural vibration, equation of vibration will always be simple harmonic. Simple harmonics means it will be in the form of like a sin omega t plus phi or a cos omega t plus phi, where a is the amplitude, omega is frequency in radian per second, and phi is phase angle. So can I say general equation of this equation of this x is simple harmonics, means it will be like this: a sin omega t plus phi, and since it is natural vibration, instead of omega you can write omega n. And here a and phi are boundary condition. Right now I don't right now I cannot tell what is their value. For that boundary condition is required. But I have calculated omega n. Omega n is 24.76 t plus phi. If instead of that it is written in form of cos also, that is also correct. Okay. Now we will find boundary a and phi. But before that, now first try to eliminate the option with this. Natural frequency in radian per second is 24.76. So can I say in the term which is either sine or cos, in that term the coefficient of time should be 24.676. So in the option in which the coefficient of time is not this value, that option will be incorrect. Like here I can directly eliminate options C and D, because omega n is 16 na. But out of A and B, which option is correct? Because both might be correct, because this condition is satisfying in both the diagram. Omega n is 24.76. So now out of A and B, which is exactly correct? For that we have to find the value of A and phi. And for A and phi we require boundary condition. And here I am having two boundary conditions. What are those boundary conditions? Firstly, can I say this at this I am displacing this mass from this, and after that at this position I am releasing this from rest. So firstly, can I say the initial displacement of this mass, initial displacement at t equal to 0 is 10 mm. If you will take in mm, is 10 mm. Initial displacement is at a equal to 0. Second, can I say the initial velocity of this mass is 0 because I am releasing at this location at this instant from rest, so velocity is 0. So here we are having two boundary conditions. What are those boundary conditions? At t equal to 0, can I say displacement x is equal to 10 mm. Second, at t equal to 0, the velocity means x dot is equal to 0. Okay. So one boundary condition I am relating to displacement. Suppose this equation is 1. Other boundary condition I am having related to velocity, which is x dot is 0. So write the equation of x dot also. It will be differentiate this equation with respect to time. So it will be a. Now differentiation of sine is cos 24.76 t plus 5, and I will multiply separately this equation with the coefficient of time, which is 24.76. So into 24.76, equation 2. Now use these two boundary conditions. So first, since at equal to 0, velocity is 0, so I am using this. So in equation 2, what I am putting, I will discuss one more trick to solve this. At t, put 2 equal to 0 and x dot equal to 0. So x dot equal to 0 is equal to a into 24.76 cos 24 at t equal to 0 now. So this part will be 0. So it will come cos phi. Yeah. Now see. Now a cannot be 0 na, because if a is 0 means no vibration is occurring, because x will always be 0. So if this is not 0, it is 0 only possible when cos phi is 0. And if cos phi is 0, can I say one possible value is phi will be pi by 2. So here phase angle is coming pi by 2. Okay. Now I am putting the value of phase angle in equation 1. So you will get the equation of x in terms of a sine 24.76 t plus phi, and phi is pi by 2. Now can I say sine pi by 2 plus alpha is nothing but cos alpha. So this is a cos 24.76 t. So this is equation 3. But still we have to calculate the value of capital A. Okay, and how we can calculate? So we know at t equal to 0, x is equal to 10 mm. I am taking in mm. So here put t equal to 0, x equal to 10. So 10 a cos 0, it will be cos 0, and cos 0 is 1. So from this I am getting the value of a equal to 10 mm amplitude. So finally the equation of x will be 10 cos 24.76 t. This is the equation of x. 10 cos 24.76 t, matching with which option? 10 cos 24.76 t, matching with option B. Clear? Another way now, it is 100% sure either A will be correct or B will be correct. So what you can see now, out of these two, which is correct? See, we know at t equal to 0, x should be 10 mm. Now here if we put t equal to 0, x is coming 0 because sine 0 is 0. So A cannot be correct. Use elimination method. Now we have only left with option B, so B will be correct. Similarly, you can also check that at t equal to 0, x dot should be 0. So if you calculate now x dot from this equation, you will get that condition will satisfy. In that equation, if you put t equal to 0, you will get x dot 0. Okay. So by elimination, you can calculate this in 1 second. First calculate omega n. So I eliminated this. Now use boundary condition. At t equal to 0, x should be equal to 10. Here it is not satisfying, so A is incorrect. So only left option is B. So therefore for this question, correct option is option B. So this is the elimination approach. Clear? Yes. Now moving to next question. This is the question. This is also good question. What this question is saying, the natural frequency of the system suspended by two identical springs of stiffness K as shown in figure is given by omega n is equal to a root K by m. Okay, this is typing error. Now both the spring makes an angle 45 degree with the horizontal. Good. Now, then what should be the value of A? So examiner is saying if the natural frequency of this system is a root by K by m, so what is the value of A? So what I am doing, from this diagram I am calculating exact value, exact expression of omega n. Okay, for this question. Then I will equate that with this expression, you will get the value of A also. Okay. Now here, whenever this type of question is coming, it is a spring mass system. But you can see these springs are not aligned in the direction of vibration of mass. See, here now if diagram is given like this, means this mass is vibrating in vertical direction. Okay. So if mass is vibrating in vertical direction, so here if you see now, this spring are not aligned in the direction of vibration of mass. So whenever this type of question is coming now, So what we'll do, we'll draw the equivalent diagram of this diagram. Okay, and in equivalent diagram what we do, we replace this spring by equivalent spring. Okay, and equivalent spring we aligned in the direction of vibration of mass. But equivalent spring, if you are aligning in the direction of vibration of mass, so we need to change the stiffness of equivalent spring. Now what should be that change the stiffness? So here I am explaining. See, first of all, this is mass m. Now what we'll do, we'll align this spring in the direction of vibration of mass. Okay, so suppose this is spring. Now to align this spring in the direction of vibration of mass, we need to change the stiffness of spring. For that now, what you have to do, first calculate the angle of this spring from the direction of vibration of mass. Right now mass is vibrating in vertical direction. So calculate the angle of this spring from vertical. Why I am calculating from vertical? Because vibration is occurring in vertical direction. Right now this angle is 45 degree because this entire is 90, this is 45. So it will also be 45 degree. Yes. What is this angle? It is representing the angle of spring from the direction of vibration of mass. Yes. After that, if this angle you have calculated, suppose this angle is theta for understanding. Now align this spring in the direction of vibration of mass. It will be like this. Now after aligning like this, now we'll change the stiffness of the spring. And that change in stiffness will be, if the angle of spring from the direction of vibration of mass is theta, so change in stiffness will be k cos square theta. Like here angle is 45 degrees, so change in stiffness will be initial this stiffness is k, so it will be k cos square 45 degree. Now cos 45 is 1 by root 2, its square will be 1 by 2, so ultimately this change in stiffness is k by 2. Same logic you can apply for this spring also. First see the angle of this spring from vertical, because mass is vibrating vertical action, again it is 45 degree. So now I will align this spring in the direction of vibration of mass. After that we'll change the stiffness. That change in stiffness will be k, this angle 45 degrees, so k cos square 45. Now cos 45 1 by root 2, its square will be 1 by 2. So how much it is coming? 1 by 2. Okay. Now when you arrange the spring in the direction of vibration of mass, so after that we can calculate equivalent spring by using series parallelization. Okay. In spring mass system, whenever only one mass is arranged, you can calculate omega n by equivalent stiffness method. Equivalent stiffness formula to calculate omega n is root ke by m. For that first I am calculating ke, which is equivalent stiffness. Now here you can see this spring and this spring are parallel to each other. And in parallel arrangement, what is the formula to calculate k equivalent? Just add the individual stiffness of individual spring, you will get overall k equivalent. So this spring is k by 2. This is also k by 2. So how much overall k is coming? K. So now what is the expression of omega n? It is root over ke by the value of mass m. Root over ke is k by m. Okay. Okay. Now examiner is giving omega n is a root k by m. So just equate both of these expression. So from this we will calculate a now. A is coming exactly equal to what? Okay. So for this question, the value of a is coming 1. Now examiner is asking round up to 2 decimal place, but it is coming into integer, means it is already correct up to 2 decimal place. So this is correct answer for this question. So we can solve this type of question like this. Clear? Now moving to next question. Yes, this is also very good question. It is numerical answer type question. What this question is saying? The natural frequency of the spring mass system shown in figure is given below. See, this spring of stiffness K1 is attached with this mass, which is 6 kg. This is rigid link. This mass is mass 2, which is 4 kg. This is stiffness K2, which is 20 Newton per meter. Okay. If two different masses are connected with each other like this through rigid link, then first of all the degree of freedom of this system will be 1. Sometimes student to think it is degree of freedom of this system is 2. No, it is 1. If between these two masses, if any spring is attached, if this link is not rigid, then the degree of freedom of that system will be 2. Okay, this type of question will come later. But I know degree of freedom of this system is 1. I can prove also how. See, suppose I am taking displacement of this mass from mean position is x. So see, if this mass from mean position is x, so this spring will also elongate by x, because this spring is coming between fixed and mass. Now since between them there is rigid link, so it cannot deform. So if this mass is going in this direction by x, this mass will also go in this direction by x, because this rigid link cannot deform. So displacement of this spring is also x. And if displacement of this spring is x, compression of this spring will also be x. So if you see, if I mention the displacement of mass 1 during vibration, so I am able to tell the displacement of the second mass also, displacement of this spring also. it means the degree of freedom of this system is 1. Okay. And if degree of freedom is 1, for that 1 degree of freedom system, we have to calculate natural frequency of this system. Now here now by using energy method, if you studied in the, I had discussed that those method in the class, you can solve this problem. But here now if you apply your aptitude now, so how to solve this type of question directly I am discussing. See, whenever this type of question is coming now, just draw the equivalent diagram of this side of this type of system. How you can draw now? See, they are connected with rigid link now, both the masses. So what you can do now, this entire portion or entire mass you can consider as a single mass, which is single mass say m, which is equal to m1 plus m2, because now displacement of this entire masses, both masses are same. Okay, when they are connected with rigid link. So what you can do now, in equivalent diagram you can draw like this. First of all, this stiffness is K1, which is 20 Newton per meter. I am replacing this system with single equivalent mass, which is m. Now beside this spring is attached, whose stiffness is K2, and K2 is 20 Newton per meter. Now what will the value of this mass m? It will be equal to m1 plus m2. Right now m1 is 6 plus 4, that is 10 kg. Why I am able to do like that? Because see, the displacement of both masses from mean position is x. Okay, so can I say displacement from mass m1 plus m2 will also be x, and if this combined assembly is going in this direction by x, this spring is contracted by x. Here also, if this combined mass is going in this direction by x, this spring will also contract by x. Similarly, if this combined mass is going in this direction x, this spring will elongate by x. Similarly, this combined mass, which is m1 plus m2, if it will go this direction by x, this is also elongating by x. So its equivalent diagram will be like this. Now, whenever equivalent diagram is like this, now you can use KE method, because now after drawing this equivalent diagram, in this diagram only one point mass is coming, and this is spring mass system. And for spring mass system, when in that system only one point mass is attached, the formula to calculate omega n is root over K equivalent upon m. So m is 10 kg. Now how will calculate K equivalent? So whenever now in a spring mass system mass is attached at the middle, so we had discussed already, again I am repeating, then is stiffness of this side system and equivalent stiffness of this side system will always be in parallel arrangement. Okay, right now equivalent stiffness of this side system is K1, equivalent stiffness of this side system is K2, so they will be in parallel. And since 1 and 2 are in parallel, how we can calculate K equivalent? In parallel arrangement, formula to calculate K equivalent is add the stiffness of individual part, means it is K1 plus K2. Right now K1 is 20 plus K2 is also 20, so how much K equivalent is coming? 40 Newton per meter, and the value of this mass is 10 kg. So from this we will calculate omega and you will get natural frequency in radian per second. It will be root over Ke, which is 40 upon mass, which is 10. So omega n is coming root 4, that is 2 radian per second. So natural frequency of this system in radian per second is coming 2 radian per second. Okay. So examiner asking, you see the unit in radian per second. So for this question, the correct answer is 2 radian per second. Okay. Now moving to next question, this question. This is also a good question. This is multiple choice question of GATE Aerospace 2014 containing 2 marks. See what this question is saying. The 1 kg mass is hanging from a spring of stiffness 500 Newton per meter attached to a massless symmetric beam of length 0.6 meter. It is shown in figure. The moment of inertia of the beam about bending axis, means ultimately it is about neutral axis, is 8.33 into 10 to the minus 10 meter to the power 4. Young modulus is 210 gigapascal as shown in figure. What is the fundamental natural frequency of this system in radian per second? Okay. So see, length of the beam is given, very good. The Young modulus of this beam, what I am writing here, it is for beam material, is 210 gigapascal. In Pascal, I am using SI unit, so it will be 210 into 10 to the 9 Pascal. Area momentosity of the cross section of beam about bending axis, means about neutral axis, is 8.33 into 10 to the power minus 10 meter to the power 4. Yes. So we have to calculate natural frequency of this system. This mass, so suppose it is m, is 1 kg. Okay, and beam is massless, na? So whatever vibration will occur in the beam, that will be transverse, that will be natural vibration, because of single degree of freedom system, because beam is massless. Now see, Actually in IM beam transverse vibration will occur. See, because the spring is vertical, directly it is connected with this mass, so this mass will vibrate well like this. And when this mass is vibrating like this, just try to feel this point of the beam will move up and down. And if it is moving up and down, this beam will bend. And if beam is bending during vibration, means transverse vibration is occurring in the beam. Now here what I am drawing the equivalent diagram of this structure. Equivalent diagram means, see, this spring is directly attached to the mass. Okay, and we know the stiffness of this spring. So to calculate the equivalent, to draw the equivalent diagram and to calculate equivalent stiffness, what I am doing, first we will calculate the stiffness of this system, because stiffness of this spring is already known. See, and this system is containing beam, and in beam transverse vibration is occurring. So in transverse vibration, the stiffness due to which restoration occurs is known as bending stiffness. So indirectly we can say we have to calculate the bending stiffness of this beam. Suppose bending stiffness of this beam is KB. Once we have calculated bending stiffness, then we can easily draw the equivalent diagram of this system and we can calculate overall K equivalent. But before that, first I need to calculate bending stiffness. Now what is the method to calculate bending stiffness? So here I am discussing first how to calculate KB. Now what is the method now? See, this beam whose length is 0.6 meter. Good. Okay. Now suppose if this spring is not there, because right now my focus is only in the calculation of KB, then we'll attach mass M from at this location, which is the free end of this cantilever beam. This diagram drawing only to calculate KB. Okay. So whatever stiffness of this system is coming, that is not overall calculate, that is the bending stiffness of original diagram. Because here we have not considered this spring in this diagram. So this diagram I have only drawn to calculate KB. Yes. Now how we can calculate KB? So just think, in this beam at the location where mass is attached, this I am discussing for calculation of KB. At this point, if you will apply a transverse load P, then what will be the deflection of this point due to that load P? Suppose that deflection you are presenting as delta. So can I say deflection of this point where load P is applied, due to this load P, it will be PL cube by 3I. This formula we have studied in strength of material. Whenever in cantilever beam, transverse load is applied at the free end, the formula to calculate deflection of free end is PL cube by 3I. Okay. And P by delta is known as stiffness. So bending stiffness of this beam will be 3EI upon L cube. 3I upon L cube. Okay. Since I am discussing, so I have drawn this diagram, but even without drawing diagram, you can tell this will be the bending stiffness. How? Just think like this. If this spring is not there, we'll attach mass here. Now in the beam where mass I am attaching the mass, just try to imagine in your mind, at that location, if I will apply a concentrated force P, what will be the deflection of that point? So I will apply that load in free end of the beam, and in free end of cantilever beam, if I am applying any load P, the formula to calculate deflection of free end is PL cube by 3I. And if delta is PL cube by 3I, P by delta will be bending stiffness, which is 3I upon L cube. So you can write this expression directly also. But since I have written the expression of KB, now I am calculating the value of KB. It is 3E. Use SI unit. So E is 210 into 10 to the 9 Pascal into I is 8.33 into 10 to the minus 10 upon L cube, and length is 0.6 meters, so it is 0.6 cube. So from this we'll get the value of bending stiffness of this beam. How much it is coming? 3 into 210 into 10 to the 9 into 8.33 into 10 to the minus 10 divided by 0.6 cube. You can check calculation. It is coming 2429.583 Newton per meter. Okay. So this is the expression of, thanks dost. Okay. This is the expression of bending stiffness of this beam. We have calculated. Now for bending stiffness, after calculating KB, now we can draw overall equivalent diagram. Okay. So what we'll do now, whenever we have calculated bending stiffness of this beam, so now what we'll do, we'll replace this portion of the beam by a spring whose stiffness is KB. Okay. And the value of KB we have already calculated. This is the value of KB. Okay. Now, after replacing this beam by a spring whose stiffness KB, now we'll consider other system. Now, after that is with this end of the beam, this spring is attached whose stiffness is K, and the value of K is known. It is 500 Newton per meter. Good. Now below this mass M is attached, and the value of mass M is 1 kg. So when I had drawn this equivalent diagram, so in this equivalent diagram, from this equivalent diagram we can calculate overall K equivalent. How? Suppose this spring I am referring as spring 1 whose stiffness is bending stiffness KB. This I am referring as spring 2. So you can see both of these spring is having end-to-end connection, and below this mass is attached. And whenever spring are connected like this, having end-to-end connection, means these spring are arranged in series. And since they are in series, so now I can calculate their equivalent stiffness. How? So in this actual beam, when we have drawn equivalent diagram, we have concluded that 1 and 2 are in series. So now I can calculate their equivalent. So their equivalent stiffness I am representing as Ke. And what is the formula to calculate equivalent stiffness in series arrangement? Okay, right, by taking reciprocal, like 1 upon Ke will be equal to 1 upon K1, and K1 is bending stiffness of the beam, by which I am denoting as KB, plus 1 upon K2. K2 is the spring of spring, stiffness of this spring, which we are denoting with K. So from this you can calculate Ke. 1 upon K equivalent, it will be equal to 1 upon KB. KB is bending stiffness of the beam, which is coming 2429.583 plus 1 upon K. K is the stiffness of this spring, which is coming 500 Newton per meter. So from this we can calculate overall K equivalent. Now calculation in your part, how much it is coming? 1 upon 2429.583 plus 1 upon 500, yes. So 1 upon 500, it is 1 upon K, then inverse. K is coming 414.664 Newton per meter. And after calculating K equivalent, we can calculate natural frequency of this entire system in radian per second, that is omega, and it will be root over Ke upon the value of point mass m. Yes, root over Ke. Ke is 414.664 and upon value of mass m, and right now the value of mass m is 1 kg. So how much omega, and that is natural frequency of this system, is coming in radian per second. It is coming root over 414.664 divided by 1. Okay, 20.363 radian per second. Okay. Okay. In YouTube also I have completed this particular topic also, that is transverse vibration of beam. Okay. If you want, you can watch those lectures also. So 20.363 radian per second. Is asking radian per second, and it is coming 20.36, matching with which option? Option B. So for this question, the correct option or answer is option B. Okay. Now moving to next question. This is also simple question. What this question saying? In a spring mass system shown in figure, the value of point mass m is 3 kg. Spring stiffness are 20 kilonewton per meter. Stiffness of each spring are same, which is K, and K is 20 kilonewton per meter. Then exam asking natural frequency of this system in hertz. For that, now first calculate equivalent stiffness of this system, and for that you can use series parameters. Suppose this is spring 1, this is 2, this is 3. Okay. Okay. Now value of K, I am directly calculating with value, is 20 kilonewton per meter. It is also 20 kilonewton per meter. It is also 20 kilonewton per meter. Okay. So see, we know whenever in any system, if the spring are directly attached to the mass, you can always use series arrangement. But before that, which spring are in series, which spring are in parallel, how will conclude that? So see, whenever mass is coming at the middle, so we know the equivalent stiffness of this side system and equivalent stiffness of this side system will always be in parallel arrangement. So see, this side only one spring is coming, so we can say we already know the equivalent stiffness of this side system, it is 20 kilonewton per meter. But now we need to calculate equivalent stiffness of this side system. So this side system, 2 spring 1 and 2 are coming, and they are having end-to-end connection. So can I say they will be in series arrangement? So first I will calculate equivalent stiffness of 1 and 2, so that is K12. And how I can calculate that? So you can see here 1 and 2 are having in series arrangement because they are having end-to-end connection. So since 1 and 2 are in series, so by using the series formula, we can calculate K12. K12 is stiffness of both of these spring, which is nothing but equivalent stiffness of this side system. Now since they are in series, use this reciprocal formula. So their equivalent I am representing as K12. So 1 upon K12, it will be equal to 1 upon K1, which is 20 kilonewton per meter, plus 1 upon K2, which is again 20 kilonewton meter. From this you can calculate K12. Calculation is your part. If you simplify this, it will come 10 kilonewton per meter. You can check. Okay. Now K12 is equivalent stiffness of this side system, and K3 is the equivalent stiffness of this side system, and you can say they are in parallel arrangement. Okay. So now can I say the K12 and spring 3 are in parallel, and since are in parallel, so I can calculate their K equivalent. Now their K equivalent stiffness I am representing as K equivalent, because after calculating equivalent of K12 and 3, no other spring are left. So that will be overall K equivalent, which I am representing as simply as Ke. And since they are in parallel, so I will add the stiffness of this spring. That will be equivalent stiffness of this system, which I am representing as Ke, and Ke will be equal to K12 plus stiffness of spring 3, which is K. Now K12 is 10 plus K is 20. So how much overall K equivalent is coming? It is 30 kilonewton per meter. In Newton per meter, 1 kilonewton is 1000 Newton. It is 30,000 Newton per meter. I am converting in Newton meter per meter, because when you calculate natural frequency, you will put the stiffness in SI unit, that is in Newton per meter. Yes. So after calculating K equivalent, now we can calculate natural frequency of this system in radian per second, that is omega n. It will be root over Ke upon the value of mass m. Now root over Ke is 30,000 Newton per meter, and the value of mass m, it is given in the question, it is 3 kg. So from this we can calculate omega and how much it is coming. Root over 30,000 divided by 3, it is coming 100 radian per second, but it is in radian per second. But right now examiner is asking natural frequency in hertz. So if we calculate natural frequency in radian per second, then what will be natural frequency in hertz? Suppose that I am denoting as Fn. So relation is Fn is always omega n upon 2 pi. This is nothing but natural frequency in hertz. How much it will come? Omega 1 is 100 divided by 2 pi. So how much natural frequency in hertz is coming? It is 100 divided by 2 divided by pi. Is it coming? 15.915 hertz. So for this question, the natural frequency in hertz is coming 15.915 hertz. So examiner asking in hertz, but round up to nearest integer. Now round up mathematically, if you round up 15.915 up to integer, can I say it will be 16? This is mathematics, na? If it is after point, it is where this value is greater than 5, so I will increase this value by one amount, so it will be 16. Round up mathematically. So round up to nearest integer for this question, the correct answer is 16 hertz. Clear? So this is the answer for this question. Okay. Now moving to next question. Now till now we have discussed the questions of single degree of freedom vibrating system, where in that system natural vibration was occurring. Now what I am doing, I am taking those questions in which again it is single degree of freedom system, but damped vibration is occurring. So related to this, we will discuss some PYQs. So discussing one by one. See what this question is saying. This is first of all multiple choice question. So out of this 4 options, one option will be correct. What it is saying, a spring mass damper system with a mass of 1 kg, okay, is found to have damping ratio. Damping ratio means damping factor is given 0.2. And natural frequency, whenever in question natural frequency is given, so it is natural frequency when means it is the frequency when there is no damper attached, means the frequency of free undamped vibration we are referring as natural frequency. Okay, actual frequency, vibration of actual frequency can be different, but natural frequency means when in the system free undamped vibration will occur, the frequency of that frequency I am referring as natural frequency. And it is mentioned it is 5 radian per second. Then what will be the damping coefficient of this system, which I am representing as C. And whenever the question of damped vibration is coming, and if diagram is not given, so always consider general diagram. General diagram, because whatever formula we have studied now, we have studied with respect to general diagram means a spring is the of stiffness K is attached parallel to the damper of damping constant C, and below this are directly a point mass M is attached. So whenever diagram is not given, always consider this diagram, because formula which we have remembered for this diagram. Now here it is given the mass is 1 kg. Yes, it is having damping factor 0.2. Natural frequency means omega n. Omega n, it is 5 radian per second. Actual frequency will be different. See, in free damped vibration, if vibration is occurring, actual frequency we denote as omega d. Okay, and vibration will occur whenever damping factor, that is zeta, is less than 1. Right now it is less than 1 means vibration is occurring. And formula to calculate actual frequency omega d is omega n, which is natural frequency, root over 1 minus zeta square. So if examiner is asking omega d, you can calculate that also. Okay. But right now examiner asking damping coefficient of this damper, that is value of C. How we can calculate damping coefficient? So since zeta is given, and for damped vibration, what is the formula to calculate zeta? Okay, we are having two formula to calculate zeta. Okay, for general case, either it is C upon 2 root over Km, or you can write this formula like this also, C upon 2m omega n. Both formula are same, but this formula is for general case, and whenever diagram is not given, we will consider general case. Okay, So right now what I'm doing, I'm using this formula because zeta is given, m is given, omega n is given. So from this I can calculate C. Yes. Instead of that, you can use this formula also. How? Since omega n is given, omega n is root k by m. From that calculate k, then put here. So from this also you can calculate C. But why to go in the calculation of k? Because when I am having direct formula of zeta in terms of C m omega n, so I am equating this zeta with C upon 2 m omega n. Okay. Now zeta is 0.2. C I want to calculate upon 2 m. Mass is 1 kg into omega n. Natural frequency in radian per second is 5. So in this only one unknown C is coming. So how much it is equal? 0.2 into 2 into 5. It is coming 2, and SI unit of damping coefficient is Newton second per meter. So for this question, the value of damping coefficient of the system is coming 2 Newton second per meter. Okay. Matching with this option A. Here unit is also important because here also 2 is written. So see, remember the SI unit of damping coefficient is Newton second per meter. How we can remember this? See, C, what is damping force? It is C into velocity, and SI unit of damping force is Newton. So can I say unit of C will be unit of force, that is Newton, divided by unit of velocity, and unit of velocity is meter per second. So actually the unit of C is Newton per meter per second, which we can also write like this, Newton second per meter. So as per this unit, C is coming 2 Newton second per meter, which is mentioned with option A, matching with option A. So for this question, the correct answer is A. Yes. Now this question. This is multiple choice question again. What this question is saying, in a spring mass damper single degree of freedom system, the mass is 2 kg. So mass m is 2 kg. And the undamped natural frequency is 20 Hz. So undamped natural frequency means, again, if there is no damper, then what will be the frequency of that system is again? Means it is omega n, but I am denoting this as Fn because right now it is given in Hertz, 20 Hertz. You can convert that in radian per second, and whatever it will come in radian per second, that will be omega n. If required, I will do that conversion. Then exam asking critical damping coefficient of the damper, means we have to calculate damping coefficient of the damper C. Good. But when damping is critical damping is nothing but the damping when damping factor is 1. See, at critical damping always zeta will be equal to 1. Okay. And at critical damping, whatever is the value of damping coefficient is coming, you can also refer that as critical damping coefficient because it is the damping coefficient of the damper at critical damping. So right now we know the value of zeta. Okay, and we have to calculate C. Now what a formula again I can I use? See, we know zeta is C upon 2 m omega n. So from this, and zeta is 1 because it is critical damping. So from this I can calculate C because m and omega n is given. M is 2 kg. Now omega n is natural frequency of the system in radian per second, but right now it is given in hertz. So convert that in radian per second. Now we know if frequency in hertz is Fn, it will always be equal to omega n upon 2 pi, where omega n is frequency in radian per second. So from this, can I say omega n is 2 pi Fn? Yes. Now 2 pi Fn. Fn is 20. So how much it is coming? Omega n 400 pi radian per second. Why I am calculating in terms of pi now? Because options are given in terms of pi. So keep pi as pi. Okay. Now, so C, can I say zeta equal to 1? That is equal to C upon 2 m. M is C upon 2 m omega n. M is 2 kg and omega n is 400 pi. So from this we can calculate C how much it is coming. 2 into 400, that is 1600 pi Newton second per meter. So for this question, the value of damping coefficient of the damper is 1600 pi Newton second per meter. 1600. Do I have done some calculation mirror? Omega Fn is sorry, there is calculation error. Omega n is 2 pi Fn, 2 pi. Fn is 20 na, so 20 into 2 it will be 40 pi. This is calculation error from my side, 40 pi. So actually omega n is not 400 pi, it is 40 pi. This is calculation error. So it is 40 pi. Okay. So it will come, C will come 40 into 2 into 2, that is 160 pi Newton second per meter. So that was calculation error. So the value of damping coefficient of the damper is coming 160 pi Newton second per meter, matching with which option? Option A. So for this question, the correct option is option A. Okay. Now moving to next question. This question. What this question is saying, for the damped spring mass system, the mass is 10 kg, stiffness is 10 to the power 3 Newton per meter, and damping coefficient is 20 kg per second. The ratio of amplitude of oscillation of the first cycle to the fifth cycle is, okay, to the fifth cycle is. So I am discussing this question. What this question is saying, or before discussing this question, now what I am doing, I am making a overall summary of also general spring mass system when damped vibration is occurring in that system, because now it will be better. General spring mass system is mass is directly attached to the spring, parallel to this damper is attached, whose damping coefficient is C. If this diagram is coming, okay, whenever diagram is not given, we will consider general case. The governing equation of vibration will always be like this. Suppose if displacement of mass from mean position is x, na, so this equation will be like this: mx double dot plus cx dot plus kx equal to 0. Means in this equation, the coefficient of x is k, coefficient of x dot is c, which is damping coefficient of the damper, coefficient of x double dot is m, which is mass of the system. Now to find its solution, now mainly we calculate two things. One is damping factor of the damper, which damping factor which I am denoting as z. The formula calculated zeta is C upon 2 root over Km or C upon 2m omega. This formula we were using also. Sometime examiner can ask one more factor which is known as degree of dampness. It is nothing but zeta square. So if zeta we have calculated, you can calculate degree of dampness also. Second, one more parameter, omega is not actual frequency. It is the frequency when undamped vibration. Suppose if there is no damper, then what frequency will come? That is known as natural frequency. And for natural frequency of general spring mass system, we already know it is root k by m. Now why I am calculating this? Because now we can make entire solution related to damped vibration only in terms of zeta and omega n. Now here, if we calculate zeta, what is the value of zeta? That is very important. If zeta is coming less than 1, that case is known as under damping. And what is the meaning of under damping? Under damping means in free damped vibration, if it is the case of under damping, means in that case vibration will occur, but the amplitude of that vibration will reduce with time. Here vibration will occur, but the amplitude of vibration will reduce with time. Here graph will be like this. Yes. Now for this case, if you will find the solution, or that is equation of x is a function of time will be like this. First of all, here one simple harmonic term will come, A sin omega t plus phi. But since it is damped vibration, so frequency of damped vibration I am denoting as omega d. So here instead of omega d will come. So actual frequency of damped vibration is not omega n, it is omega 2. But what will happen, since here damping is there, in under damping vibration is occurring, but there is some damping. So damping will ensure that amplitude of vibration is reducing with time. So along with this harmonic term, with this one exponential decreasing function comes. And that exponential decreasing function is e to the power minus zeta omega n t. These things we have discussed in the class. So this is the equation of x. Okay, so if examiner asking this equation, this is the equation. But generally examiner asks frequency of this damped vibration. So can I say frequency of damped vibration? But this is always only valid when zeta is less than 1. Is omega d, then formula to calculate this is omega n root over 1 minus zeta square. Now remember this formula. So if examiner asking calculate omega d, this is the formula. But this is only valid when zeta is less than 1. Okay. Yes, it is in radian per second. If you calculate radian per second, you can calculate frequency in hertz also, that will be omega d upon 2 pi. You can calculate time period also, that will be 2 pi by omega d. Okay. Now in damped vibration, when it is the case of under damping, one more important parameter comes, which is known as logarithmic decrement. What is logarithmic decrement? That I am denoting as delta. Formula to calculate this is 2 pi zeta upon root over 1 minus zeta square. Okay, this all concepts are only valid when zeta is less than 1. Okay. Now why it's important now? Because see, actually in damped vibration I had discussed that displacement in 2 consecutive cycle will always reduce, or amplitude of 2 consecutive cycle will be different. Reduce, continuously it will decrease. So here now if we calculate the ratio of amplitude in corresponding cycle or consecutive cycle. Okay. Or not only about amplitude, whenever you are taking the ratio of displacement of 2 point, when gap between them is one time period. If gap is one time period, means the gap between them is one cycle. So whenever gap is one cycle, now the displacement ratio is always constant. Like suppose I am calculating ratio xn minus 1 upon xn. Like you can calculate x1 by x2 also. Okay, time gap should be one time period. X2 by x1 also. Time gap should be one time period. Okay, and out of this ratio now, the amplitude which is coming later, okay, that I am writing below. The amplitude which is coming earlier, I am writing above. So this ratio is always constant, and that is equal to e to the power delta. Definitely it will come more than one, because later displacement is less and earlier displacement is more. So whenever time gap between them is one time period, and if you are writing earlier amplitude or displacement above side, this will be equal to, this ratio will be equal to e to the power delta. But what will happen when the gap between them is n cycle? Like suppose I am calculating x2 by x5 just for understanding. What is the time gap between them? It is 5 minus 2, that is 3 time period. So this ratio, if the gap between them is one time period, the ratio is e to the power delta. If gap is 3 time period, this ratio is e to the power 3 delta. If in this ratio gap is n time period, then this ratio will equal to e to the power n delta. Just remember this. And delta is logarithmic decrement, whose formula is this. Okay. Now we can easily solve this question. See what this question is saying. In a spring mass system, the mass is 10 kg. Yes. Today, I have only made the summary related to under damping. Na? Stiffness is 10 to the power 3, that is 1000 Newton per meter. Good. And damping coefficient C is 20 kg per second. See, kg per second is nothing but Newton second per meter. Dimension wise, both are same unit. So instead of Newton second per meter, if C is given in kg per second, that is also correct. Okay. Then exam asking what is the ratio of amplitude of first cycle to that of fifth cycle. Suppose amplitude of first cycle I am representing as 1. The amplitude of fifth cycle I am representing is 5. So it is x1 by x5. Okay. And definitely if exam asking amplitude of first cycle and fifth cycle, means here some vibration is occurring, and vibration will only occur when zeta is less than 1. So here if we calculate zeta, now I am 100% sure it will come less than 1. Automatically, but it will come less than 1. But here see, in this ratio, the time gap is 4 time period, 5 minus 1, 4. So can I say this ratio will be equal to e to the power 4 delta, and this we want to calculate. So to calculate this ratio, you need to calculate delta first, and to calculate delta, we need to find zeta first. So first I am finding zeta, and whenever diagram is not given, consider general case, and for the general case formula to calculate zeta is c upon 2 root over km or c upon 2m omega n. So write down in question, c km values are directly given. So I am equating zeta with c upon 2 root over km. Okay, now c is 20 upon 2 root over km. K is 1000 into m is 10 kg. So from this you will get the value of zeta, how much it is coming. 20 divided by 2 into root 1000 into 10. Is it coming 0.1? Yes. And after calculating zeta, now we can calculate logarithmic decrement, that is delta. And the formula to calculate delta is 2 pi zeta upon root over 1 minus zeta square. Okay. Now 2 pi zeta, zeta is 0.1 upon root over 1 minus zeta square. Zeta is 0.1, so it's a square. This topic is favorite question in GATE. You will find a lot of question from this. It is coming 2 pi into 0.1 upon root over 1 minus 0.1 square. Is it coming 0.6315? Calculation is your part. So this is the value of logarithmic decrement. And after calculating this, we can calculate x1 by x5, which examiner is asking. It is equal to e to the power 4 delta. Yes. Now e to the power 4 delta. Delta is 0.6315. So how much it is coming? x1 by x5, it is e to the power 4 into 0.6315. This ratio is coming 12.503. Okay. So it is 12.503. Okay. Now I say round up to 1 decimal place. So if you round up 12.503 up to 1 decimal place, mathematically it will be 12.5. Okay. So this is correct answer for this question. Okay. So this type of question we can solve like this. Now again moving to next question. This is the question. See, a uniform rigid bar of mass 1 kg, length 1 meter is pivoted at A. It is supported by a spring of stiffness K, which is 1 Newton per meter, and viscous damping of damping coefficient C, which is 1 Newton second per meter. Okay, with A, this distance A is 1 by root 3 meter. Okay, the moment of inertia of this rigid bar about A, for this rigid bar, moment of inertia about A is given. Okay, it is ml square by 3. Then 𝐂𝐤𝐴 system is overdamped. It is underdamped with frequency 1 radian per second, critical damped, or underdamped with frequency 2 radian per second. See, ultimately it is type of damping first of all. So we'll calculate the value of zeta. If zeta is coming less than 1, it is underdamped. If it is equal to 1, critical damped. If it is greater than 1, it will be overdamped. Clear? Yes. But here for zeta, I cannot use C upon 2 root km formula directly because this is not general case. Spring is, see, this mass is not a point mass, na? Okay. So I cannot use C derived formula. So here in this type of question, what we'll do? First, we'll derive the equation of vibration, governing equation or differential equation of vibration. Ultimately, I am 100% sure the pattern of the equation will be like this. Okay. But coefficient can change. Because like for general case, coefficient of x is k, coefficient of x dot is k, c, coefficient of x double dot is m. And if coefficient are this is the formula to calculate zeta. For other case, what will be the coefficient now? That will come to know after derivation. Like what I am trying to say, whenever question is coming from other case, right now forgot that question. Okay, so what we'll do now, in general case, equation was like this, mx double dot plus cx dot plus kx equal to 0. In other case also, equation of pattern will be like this, x double dot will come, x dot will come, x will come. But here I don't know about coefficient, that will come to know after derivation. So see, for general case coefficient of x was k, but for other case what will come, right now I don't know, so I am representing that is ke. K is not k, it is the coefficient of x. For general case k is k, but for other case what will be k, that will come to know after derivation. Similarly for general case coefficient of x dot is c, so here I am representing that as ce. C is not c, it can be c also, it can be c by 2 also, it can be c by 3 also, it can be cl square also. That will come to know after derivation. For general case c is c, but for other case will come to know after derivation. X dot, coefficient of x double dot is suppose me. For general case m is m, but for other case what will be me, that will come to know after derivation. But if I am writing like this, can I say now this equation is equivalent to general case, only difference instead of m is coming, instead of c is coming, instead of k is coming. For general case k was k, c was c, m was m. But for other case, what will be k, c, m, that will come to know after derivation. It's not necessary here always it will be x dot, x dot. See, if it is theta na, then it should be theta dot, it should be theta double. Then also both equation are same. Here if it is phi, it should be phi dot, it should be phi double dot. Here if it is x1, here it should be x1 dot, here it should be x1 double dot. Then all equation are same. Okay, and if equation is coming like this, what will be the formula to calculate zeta? See, for general case, zeta was c upon 2 root km. Now, then now whatever formula you have studied now, in that formula, just replace c by c, k by k, and m by me. After that, all formula will be same. Only difference, instead of c, ce will come. Instead of k, ke will come. Instead of m, me will come. Means for other case, the formula to calculate zeta. For general case, it was c upon 2 root km. Instead of that, ce upon 2 root over. Instead of k, ke. Instead of m, me will come. Same is valid for omega now. So omega is root k by m. But instead of that, it will become root ke by me. Like this. But for that, first I need to calculate ce, ke, me na. For that, we'll need to derive the equation of vibration. For this question, I am doing that. Okay. Right now, the stiffness of this spring is 1 Newton per meter. I am writing here. The damping coefficient of the damper is 1 Newton second per meter. 1 Newton second per meter. I am writing the value also. This length is 1 meter. L is equal to. And this distance A is 1 by root 3 meter. And right now question, the moment of inertia about A is given, it is ml square by 3, I think, na? And the value of mass is given, mass of the rod is 1 kg. But here don't say mass is 1 kg, c is 1, k is 1, so zeta will be c upon 2 root over km. No, it's not correct. See, if you can calculate the exact value of I also. M is 1, L is 1 meter, so 1 square divided by 3. I think it will come 1 by 3 kg meter square because it is mass inertia. Now, actually, now in this bar or beam, whatever you want to referring, rotational vibration will occur because when it will vibrate by rotating about A like this. So here rotational vibration is occurring. Okay. So what I am doing for this rotational vibration, I am deriving the equation of vibration. Na? Yes, I will use I center method. Okay. Now, first of all, now this rod is hinged at this location. So at this point, since rod is hinged, so can I say this will be the I center at this instant for the rod? Because what is I center? I center is the point about which any system or body rotates. So since rod is hinged at A, so A will be the I center of the rod. Or whenever you are using I center method now, and if it is rotating, so always calculate the mass ratio of that body whose mass is given about I center. And right now for this rod, already mass ratio about I center is given, because I center is nothing but point A. So already I about I is given. It is ml square by 3, which is the exact value we have calculated. It is 1 by 3 kg meter square. Okay. Now when this system is vibrating, so I am drawing the diagram. Okay, during vibration in which this rod has rotated by theta angle about I center. But here it is 100% sure when vibration will occur, restoration will only occur due to the stiffness of the system, but it will not occur due to gravity. This analysis is important, because see, if restoration is occurring due to gravity, then when you are deriving the equation of vibration, we will consider the weight of the system also. But when the restoration is not occurring due to gravity, then while deriving the equation of vibration, you have to nothing to do with weight. Okay, means will not consider weight. And if you are not consider weight, will also not consider static deflection of the spring in the vibration, static deflection of the spring due to weight of the system. Okay, what I am trying to say, see, how you can decide whether restoration will occur due to gravity or not. So see this weight of the system. Try to analyze, is it supported by this spring or not? Simply see, if this spring are not attached here, this rod cannot be like this, it will rotate like here, because gravity will rotate this. Means can I say the weight of this rod is supported by spring, and whenever weight of rod is supported by spring, so due to weight there will be some static deflection in the spring. And since due to weight there is some static deflection in the spring, so first of all weight, and second static force due to static deflection of the spring will counter each other effect. And since they are countering each other effect, means in this question there is no role of gravity of restoration. Okay, how they are countering, you need not to go in the calculation of that part. Since there is static deflection in the spring due to weight, means they will counter each other effect, means there is no role of gravity in the restoration. And since there is no role of gravity in the restoration, while deriving the equation of vibration, neither will consider the weight of the system nor will consider the static deflection of the spring. Means whatever deflection I will take, that is the deflection from mean position. But you need not to bother about the static deflection of the spring. They will counter each other effect. How they are cancelling, don't bother about that. So see, I am taking any position in which this rod is rotated by theta angle during vibration about I center. But this theta is from mean position. What is the displacement at mean position? You have not to think about that. Right now I taken theta clockwise. Okay, good. Okay. So here spring is attached, so it will reflect. Suppose this displacement is x1, again it is displacement from mean position. Here damper is attached, so suppose displacement of this point from mean position is x2. You can find the expression of x1 and x2 in terms of theta. How? If we will say this triangle, can I say x1 will be equal to this distance is a. So for whenever we are doing the equation, deriving the equation of vibration, we are deriving for small oscillation. Small oscillation means theta is very less, and when theta is less, x1 will be nearly equal to a theta. Actually, after deflection, this distance is a. So we'll calculate x1. X1 will come a sine theta. But for small oscillation, sine theta and tan theta are nearly equal to theta. So for small oscillation, I am referring x1 is equal to a theta. Okay, good. Similarly, x2 is the displacement of this point from mean position. It will be, so distance of this point from I center is L or 1 meter. So it is 1 theta. You have numeric value also. A is 1 by root 3. So you can actually put the value 1 by root 3 theta. And it is 1 theta. I am directly putting the value. Okay. Yes. Now I am drawing the FBD of this rod. Okay. Here spring is attached. I am cutting from this location. Here damper is attached. I am cutting from this location. If you want now, you can directly draw the FBD here. Just for understanding, I am drawing separate diagram. This distance is 1 by root 3 meter, and this entire distance is L, which is 1 meter. This is the location of I center. Now I will draw the FBD. Mainly we will apply three forces or movement, three type of forces. One is restoration. Since here restoration is occurring due to stiffness, so apply restoring force due to the stiffness of the spring. And see, the formula to calculate restoring force due to the stiffness of the spring is always K into deflection of the spring from mean position. Okay, like here stiffness of this spring is K, its displacement from mean position is x1. So restoring force due to this stiffness of the spring will be Kx1. K value we already know it is 1 Newton per meter. So you can write 1 x1 also, or I will put the value later. That's direction. In the body of rod, it will always be opposite to x1. Right now x1 is downward, so it will be upward. Okay. Yes, it will be upward. Okay. Now no other spring is attached, so its part is completed. Now if damper is attached, due to damper we will apply damping force. So see how we can apply damping force. See, if damping coefficient of the damper is C, so the formula to calculate damping force is C into, for damping force we see the velocity. Like suppose displacement of damper from any, for displacement of any damper from mean position is x, so its velocity will be x dot. Then damping force will be C x dot. And direction of damping force will always be opposite to velocity, that is opposite to x dot. Right now damper is attached here, and you can see the displacement of this point from mean position is x2. So can I say velocity will be x2 dot? Differentiate x2 with respect to time, that is x2 dot. So here damping force will be cx2 dot. That's it. Now direction. See, direction of damping force will always be x2 dot. And whenever we are calculating any parameter by differentiation, like x2 dot is differentiation of x2. So mathematically, whatever is the direction of x2, right now x2 is downward. So that will be the direction of x2 dot also. Reason na? Because if this direction is correct, now automatically x2 dot will come with plus sign. If it is incorrect, it will come with minus. Minus in means the actual velocity is upward, but still x2 dot will always be downward. Because see, if any value is like this 1, you can write like this also now with minus 1. So x2 dot will always be downward, means whenever we are differentiating mathematically, the direction of x2 dot will always be same as x2. So right now x2 is downward, so x2 dot will also be downward. So damping force is opposite to this, means in the body of rod it will be upward. Okay, this part completed. Now, okay, now we will apply here inertial moment. So whenever you are using I center method, now what is the method to apply inertial moment? See, what is the I about I center for the body whose inertia is given? Right now inertia of rod is given. So what is the I about I center for the rod? That is this value which I am simply denoting as I about I. Now see the angular acceleration of this rod. See, angular displacement of the rod is theta. So angular velocity will be theta dot. Angular acceleration will be theta double dot. Okay. And since we are differentiating mathematically, so direction of theta dot and theta double dot will be same as theta. Right now theta is clockwise. So theta dot, theta double dot is also clockwise. Then the inertial moment in I center method, always to apply inertial moment at the I center, and formula to calculate inertial moment which I am applying at I center is I about I into angular acceleration. In this case it is theta double dot. So inertial moment will be I about I into theta double dot, and its direction will always be opposite to theta double dot. Right now theta double dot is clockwise, so it will be anti-clockwise. But remember, whenever you are using this method to calculate inertial moment, na, means I about I into angular acceleration. In that equation, whenever you will derive the equation of vibration, we will always take summation of moment about I center. Whenever you are applying inertial moment like this, na, so always take summation of moment about I center. So here also I will take summation of moment about I center. Now, here at I center rod is hinged, so you can say here hinge support reaction will also come. But you need not to bother about the reaction which is coming at hinge. It will not matter. Reason? Because I will take summation of moment about I center. So can I say the moment, and whenever you are calculating summation of moment, couple comes as it is in moment equation. But if it is moment due to force, the moment due to force will always be force into perpendicular distance. So the reaction which is coming at hinge support is force reaction. And can I say their moment about I center is always 0 because their perpendicular distance from I is 0. So you need not to bother about the reaction which is coming at I because their moment about I will be 0. Okay. So we will calculate summation of moment about I. And if you applied this inertial moment in the system, so after applying inertial moment, system will always be in equilibrium. Actually system is not in equilibrium, but after applying inertial moment, we can assume it is in equilibrium. So you can use equilibrium equation, but after applying inertial moment. So can I say after applying inertial moment, summation of moment about I center will be 0. So just use this. Okay. Now I am calculating one by one. First I am calculating, taking this inertial moment. Already it is a moment, so it will come as it is. It is I about I theta double dot. Here I am not multiplying perpendicular distance because it is not a force, it is a moment, so it will come as it is. Direction anti-clockwise. Now what I am doing, whatever first direction is coming now, I am adding that. Okay. Right now first direction is anti-clockwise. So right now we are adding anti-clockwise. And if you are adding anti-clockwise, subtract clockwise. Very simple. Yeah. Now moment of reaction at hinge about hinge will be 0. So we need not to bother about the reaction which is coming at hinge. Now moment of this force about I center, this force is Kx1. Now since it is force, moment will be force into perpendicular distance. So perpendicular distance, that is horizontal distance of this force from I center is 1 by root 3 meter. So moment due to this force about I center is Kx1 into 1 by root 3. Now direction, this force is like this. Now you can imagine if it is like this, about I it is rotating anti-clockwise, and right now for anti-clockwise we are using plus sign because we are adding anti-clockwise. Now moment of this force about I center, so this force is Cx2 dot, that's perpendicular distance from I center, which is 1 meter. So moment of this force about I center is Cx2 dot into 1. Now direction, so this force is like this, how it is rotating about I, again anti-clockwise, and right now we are adding anti-clockwise moment, so it will come with plus sign. Okay, so this is total moment about I center, which is equal to 0. Now just put the value. I about I center is 1 by 3, so it is 1 by 3 theta double dot plus k, value of k is 1 Newton per meter, and x1 you can see it is 1 by root 3 theta, so 1 by root 3 theta into 1 by root 3 plus c, the value of c is 1 Newton second per meter, x2 dot, so we have to find the expression of x2 dot, so we know x2 is theta. So to find the expression of x2 dot, now differentiate this equation with respect to time. So differentiation of x2 with respect to time is x2 dot, it will be equal to theta, differentiation of theta with respect to time, that is theta dot. So right now can I say x2 dot is theta dot into 1 equal to 0. Automatically it will come in general form. It is coming 1 by 3 theta double dot plus 1 into 1 by root 3, 1 by root 3, it will be 1 by 3 theta plus 1 theta dot equal to 0. Okay. Now write in the sequence 1 by 3 theta double dot, then write theta dot term 1 theta dot, that theta term 1 by 3 theta equal to 0. So it is coming in general form now, because here it is theta dot, theta double dot. So in general form, the coefficient of theta double dot is known as ME, coefficient of dot is known as CE, and coefficient of theta is known as KE. So here K is 1 by 3, C is 1, M is 1 by 3. So now you can calculate zeta. If you want to take any term common, you can take. If you want to multiply entire equation by 3 to eliminate this below term, you can multiply. Then it will be like this: 1 theta double dot plus 3 theta dot plus 1 theta equal to. This is also correct. But in that case, K will be 1. If K is 1, C is 3, K M is 1. But final answer will be same whether you are taking this equation or this equation, doesn't matter. So right now I am using this. So now I am calculating zeta. And zeta, if I had done some calculation error, please correct me. Zeta is not C upon 2 root Km. Here in other case, instead of C, C upon 2 root, instead of K, Ke upon into M, instead of M, Me. So see, here Ce is 1 upon 2 root over Ke, Me. Ke is 1 by 3 into M is also 1 by 3. So how much zeta is coming? It is it coming 1.5? Yes, and it is more than 1. See, whenever zeta less than 1, under damping, it equal to 1, critical damping greater than over damping. So since it is more than 1, so here system is over. In over damping, no. And see, if system under free vibration, if system is in under damping, that is zeta less than 1, vibration will occur. Only difference, the amplitude of vibration will reduce with time. But whenever zeta is 1, that is critical damping, or whenever zeta is greater than, that is over damping. In that case, no vibration occurs. So in this case, if exam asking vibration is occurring or not, no vibration is occurring. Okay. But right now, type of damping is over damping, means option A is correct. So for this question, the correct answer is option A. Okay. Now moving to next question. What this question is saying: during an underdamped oscillation of single degree of freedom system, in the time dependent plot, the third peak is of magnitude 100 and 10th peak is of magnitude 10, then what is the damping ratio of this damper? Okay, so see what this question is saying now. Third peak, suppose that is x3 is 100 in any unit, and 10th peak, that is x10 is 10. Then exam asking zeta. So from this information, you can calculate logarithmic decrement delta. That is, can I say x3 by x10 is given? It is 100 by 10, which is 10. Now we know the ratio of amplitude. If earlier displacement you are writing above, later displacement you are writing below. And if time gap, period gap between them is n cycle, then that ratio is always equal to e to the power n delta. So right now here see now, between them time gap is 7. Why? 10 minus 3 is 7 cycle. And since it is 7 cycle and I have written earlier displacement above side, so it will be e to the power 7 delta. Okay, and it is equal to 10. So from this I can calculate delta. Take log both sides, log of base e. So it will be 7 delta log e base e, and log e base e is 1. It is log 10, but it is log of base e na. In calculator, if we are using virtual calculator, ln is represented log of base c. log is not log of base c, it is log of base 10. Okay, so ln represent log of base c. So from this you can calculate delta. How much it is coming? Calculation you got. It is log 10 of base c, that is ln 10 divided by 7. Log e base is 1, na? So delta is coming 0.329. Okay. Now we know the formula of delta in terms of zeta. So from that we can calculate zeta. So we know what is the formula to calculate delta. It is 2 pi zeta upon root over 1 minus zeta square. Now calculation is your part. Delta is 0.329. Shifting this part this side into root over 1 minus zeta square, that is equal to 2 pi zeta. Now to eliminate this root, I am taking a square of both sides. So first of all, square of 0.329 is 0.1082 in bracket. Now here root will eliminate 1 minus zeta square. Square of 2 pi is 4 pi square. So 4 pi square, I am directly doing calculation, is 39.478 into zeta square. Square of zeta is zeta square, na? Now do calculation. 0.1082 into 1 means 0.1082 minus 0.1082 zeta square, that is equal to 39.478 zeta square. Now this minus part will come, this it will become plus, so it is coming 0.108 equal to 39.478 plus 0.1082. It is coming 39.5862 zeta square. From this we will calculate zeta. First of all, zeta square is 0.108 divided by 39.5862. It is zeta square. So square root of this will be zeta. So how much zeta is coming? Root over 0.108 divided by 39.5862. Is it coming nearly 0.052? So for this question, the value of damping factor is coming 0.052, matching with which option? Option A. Clear? Yes. Now moving to next question. Now I will eliminate some similar type of question, because lot of question we have to discuss. What this question is saying, a critically damped single degree of freedom spring mass damper used in door closing system, it is critically damped because over damped after some time due to softening of spring, and due to stiffness of this spring will change. Now if new damping ratio for over damped system, because now new system is over damped, is 1.2, so definitely it will be greater than what it is given. Then what is the ratio of original spring to the new spring stiffness, that is K original upon K new, assuming other parameter is not changing. So what examiner is saying now, earlier originally it was critically damped. Okay. Now new it is over damped and zeta new is 1.2. Okay, now formula to calculate zeta is C upon 2 root over Km. So C is not changing, 2 root over. For original case, K is K original, M is not changing. Suppose, okay. Similarly, it will be C upon, for new case also C and M is not changing. 2 root over K is changing, so K new. Now suppose this is equation 1, equation 2. Okay. Now what you can do, from this can I write root K original M will be equal to C by 2. From this can I say root K new M will be equal to C upon 2 into 1.2. Yes. Now suppose this is equation 1, this is equation 2. So what I am doing, I am calculating equation 1 divide by 2. So it will be, now if we will do equation 1 divided by 2, here it will be root this divided by 2. But out of these two expression, root M is common. In ratio, common part will always get cancelled. So even if you are not writing common part, it is okay because it will get cancelled even if you write. So can I say to LHS will be root K original upon root K new. Root M is getting cancelled. That is equal to. Similarly, see in this two term, C by 2 is common term. Okay, so this will cancel. So that I am not putting. So apart from C by 2, here 1 is coming. In equation 2, apart from C by 2, here 1 by 1.2 is coming. Now 1 by 1.2. Now 1 by 1.2 by 1.2. Okay. So ultimately it is root K original upon root 𝐾𝐻 is coming. This 1 upon 1.2 will go above side, so it will become 1.2. So take the square of both sides, you will get K original upon 𝐾𝐻. It will be the square of 1.2, square of 1.2, that is 1.44. So for this question, K original upon 𝐾𝐻 is coming 1.44. That examiner was asking round of 2 to the decimal place, so it is already coming up to 2 to the decimal place. So 1.44. So this is correct answer for this question. Okay. I am discussing this question also, but this type of question we have already discussed. So now I will eliminate similar type of question. But let's see this question. It is multiple choice question. What this question is saying: a single degree of freedom system is vibrating with initial first cycle amplitude is 5 centimeters. Suppose it is x1. Viscous damping factor associated with the vibration system is, so it is damping factor. It is 2%, means zeta is 0.02. Then they are asking what is the vibration amplitude in fifth cycle. For that, now first calculate delta, that is logarithmic decrement. We know delta is 2 pi zeta upon root over 1 minus zeta square. Very simple. Now 2 pi is zeta. Zeta is 0.02 upon root over 1 minus zeta square. Zeta is 0.02 whole square. So we will get the value of lambda. How much it is coming? 2 pi into 0.02 upon root over 1 minus, it's 0.02 now. 1 minus 0.02 square. Is it coming 0.126? Check the calculation. Now after this, now you can calculate x1 by x5. See, x1 by x5, time gap between them is 5 minus 1, 4 time period. So it is e to the power 4 delta. Okay. And x1 we know it is 5 centimeter upon x5 we want to calculate is equal to e to the power 4 delta. Delta is 0.126. So from this, can I calculate x5? x5 will be 5 divided by this. How much it is coming? 5 divided by e to the power 4 into 0.126. Is it coming 3.02? And since we have put it x1 in centimeter, it will also come in centimeter. So x5 is coming 3.02 centimeter, matching with which option? Option D. So this is correct answer for this question. Yes, this is also good question. What this question is saying: consider the free vibration response PQRS of a single degree of freedom system with some initial condition. Okay, good. Now for different damping coefficient listed below, which one of the following is correct? Overdamped, underdamped, critical damped, undamped. First of all, see the difference in un and underdamped. Undamped means there is no damping, so it is natural vibration, means vibration will occur and amplitude of vibration in each cycle will be constant. Underdamped means when zeta is here, zeta is 0, indirectly. Underdamped means when zeta is less than 1. In that case also vibration will occur, but the amplitude vibration is occurring means to and fro motion is occurring, but the amplitude of that vibration will reduce with time. But what is over and critical damp? Over and in both cases, if free vibration case is that, and in that case if it is either critical or over, in that case no vibration will occur. No vibration means what I am trying to say. Means see, in underdamping, first I am drawing the graph separate. In underdamped case, okay, the vibration will occur and amplitude of vibration will be same in each cycle. This is zeta equal to 0. Try to understand. If it is zeta less than 1, means again vibration will occur, okay, but the amplitude of vibration will reduce with time. But you can see here to and fro motion is occurring. Now whether zeta is equal to 1 or greater than 1, no vibration will occur, means to and fro motion. Suppose it is the mean line, so to and fro motion will not occur. Okay, means the system will remain this side, it will not go to other side. Whether it is zeta equal to 1 or greater than 1, it is valid in both cases. But what is the exact difference between them? So see, whether it is critical damp, whether it is over damp, in both the cases there will be no vibration. Means no periodic motion will occur. No periodic means you can understand like this. If you will disturb this spring, don't draw this for understanding, from its mean position it will release. In under damp, it will reach to my mean position, then it will go other side and it will vibrate like this. But when it is critical and over damped, it will go to reach mean position, but it will not go to other side because no to and fro motion is occurring. But what will happen in critical damping when it will reach to its mean position in minimum possible time, and when you will increase the damping further, okay, further again it will come back to its mean position. But since damping is more, damping is resistance to motion, so damping is more means it is resistance to motion is more, so system will get slow. So it will reach to its mean position, but it will take more time. So in critical and over, in both cases, first of all, vibration is not occurring. But as compared to critical, in over damping, system will take more time to reach to its mean position. First of all, in both cases, to and fro motion is not occurring. But in over damping, system will take more time to reach mean position. And in critical damping, it will take less time to reach to its mean position. Okay. Okay, that is the difference. Means here if I will draw in single case, this is zeta equal to 1. Then if we will draw the diagram for zeta greater than 1, it will be like this. It will take more time to reach to its mean position. Only see no to and fro motion. Here it is taking less time, here it is taking more time. Okay. Now you can easily do comparison one by one. First of all, see this easy graph first. See, it is simple harmonic whose amplitude is constant, means it is no damping case, means undamped, not underdamped. Undamped means no damping. So can I say this Q is linked with undamped, which is 4. So Q is linked with 4. Do use elimination method. Q is linked with 4 means option B and D we can eliminate. Then see, it is to and fro motion, here vibration is occurring, but its amplitude is reducing with time, which is underdamped case. See this graph, examiner is saying it is graph R. See arrow. So can I say this R, Q is linked with 4, R is linked with underdamped, underdamped is 2. So R is linked with 2. And since R is linked to 2, in both option A and C, R is linked with 2. So both might be correct. Okay, okay. B and D we already eliminated, na? Yes. Now, see critical over simultaneously. See, whether you see this graph P, whether you see graph S, in both cases no vibration is occurring. But in graph P, it is taking less time to reach to its mean position. But in graph S, it is taking more time to reach to its mean position. Means graph P is representing critical damping. Critical damping is 3. So P is linked with 3. And graph S is representing over damping, which is 1. So P is linked with 3. So A is incorrect. So for this question, only left option is option C. So for this question, option C is correct. This is also good question, na? Yes. Now I am discussing some question related to force vibration. See what this question is saying. A spring mass damper system is exciting by a harmonic force, means now it is the case of force vibration. And whenever force vibration, harmonic force is subjected to harmonic force, na? So this is the amplitude of force, and this is known as forcing frequency, which is inside sign coefficient of time. Now amplitude at resonance means T. We define a term which is known as frequency ratio R. Frequency ratio is always omega by omega n. Omega is forcing frequency, and omega n is natural frequency. Natural frequency when there is free undamped vibration is occurring, means there is no force, external force, there is no damping. That is known as natural frequency. For natural frequency is always root K by M for general case. For other case, it will be root Ke by Me. Okay, the frequency of natural vibration is natural frequency. And what is resonance? Resonance means R is equal to 1. Means omega by omega n equal to 1. Means omega is equal to omega n. Okay. So examining at resonance, amplitude is 1 centimeter. At half the resonance, when R is equal to 0.5, the amplitude is 0.5 centimeter. So what will be the damping ratio, that is damping factor of the system? See, in force vibration, the amplitude of force vibration we refer as steady state amplitude, because whenever we are studying force vibration, we are assuming that in force vibration in system steady state vibration is occurring. And the amplitude of steady state vibration is known as steady state amplitude, which denote as capital X. The formula to calculate this steady state amplitude capital X is F naught by K for general case. F naught is amplitude of this force, K is the stiffness of spring, upon root over 1 minus R square whole square. R is frequency ratio, which is omega by omega n, plus 2 zeta R whole square. So this is the formula to calculate capital X, suppose equation 1. Now capital X is given for two cases. First for resonance, it is 1 centimeter. For second, when forcing frequency is half the resonance frequency. Okay, so we for that amplitude is again 0.5 centimeter, so we have to calculate damping factor, that is zeta. So I am taking case 1. Case 1 means it is resonance, means R equal to 1 or omega equal to omega n. Okay, for that case capital X is 1 centimeter. It will simplify this expression for R equal to 1, it will be f naught by k upon root over. Here simply put R equal to 1, this part will be 0, I am directly doing calculation. It will be, here if we put R equal to 1, it will be 2 zeta whole square. Now you can break 2 zeta, or for this case capital X is 1 centimeter, I am taking 1 centimeter. Na? So 1 equal to f naught by k upon, if you bring outside root, it will be 2 zeta. Clear? So from this you will calculate f naught by k, it is coming 2 zeta. Suppose this is equation 1. Okay. Yes. Now case 2 is saying R equal to 0.5. How? Example for case 2, can I say omega is equal to 0.5 omega n, because natural frequency is equal to omega, sorry, resonance frequency is equal to omega n. But example saying now frequency is half of resonance frequency. So resonance frequency is equal to omega n, and half of that means actual frequency is 0.5 omega n. Means indirectly I say in case 2 question is saying R is 0.5 because R is nothing but omega by omega n, which is 0.5. And for this case capital X is 0.5 centimeter. So just put in equation 1. So capital X is 0.5, that is equal to f naught by k upon root over 1 minus R square, R is 0.5, so 0.5 square, then whole square, plus 2 zeta into 0.5 whole square. You can simplify this, it is coming 0.5 into, calculate the expression of f naught by k, because then I can equate f naught by k. It is 0.5 root over, now I am doing direct calculation, this part will come this side, na? 1 minus 0.5 square, then square of this, it is coming 0.5625 plus this part is coming 2 into 0.5, that is 1 zeta whole square, that is zeta square. Check the calculation. If I am doing calculation error, please correct that. This is equation 2. Now both equation 1 and 2 is representing since this I represent equation 1, so consider this as equation 2, this as equation 3. Now both equation 2 and 3 are representing f naught by k. So now I can equate equation 2 and 3. We'll equate, it is 2 zeta is equal to 0.5 root over 0.5625 plus zeta square. Now we'll set bring 0.5, this at 2 upon 0.5, it is 2 divided by 0.5, it is 4. So it is 4 zeta equal to root over 0.5625 plus zeta square. Now square both sides, so this root will get eliminated. So square of 4 zeta is 16 zeta square, that is equal to 0.5625 plus zeta square. Now this zeta square will come this side, it will become minus, so 16 minus 1, it is 15 zeta square equal to 0.5625. So can I say zeta square is 0.5625 upon 15, so zeta will be square root of this. So zeta is square root of this. So how much zeta is coming? Root over 0.5625 divided by 15. Is it coming 0.1936 nearly? So it is 0.1936. So see, matching with which option? 0.1936. It is matching with option D. So for this question, the correct answer is D. It is very good question. Okay. Now moving to next question. What this question is saying? A damped single degree of freedom system is vibrating under a harmonic exciting force with an amplitude ratio 2.5 at resonance. Resonance means R is equal to 1. What is the damping ratio? See, actually now it's whenever question is given like this and in force vibration amplitude ratio is represented, now it is known as, actually it is magnification factor. It is known as magnification. Examiner should write clearly it is magnification factor. But if it is written like this, na amplitude ratio, so other name of amplitude ratio is for which question you are talking about? Harry, last question. See, First, I had discussed this force vibration topic on YouTube also in this channel. You can watch those lectures because today we are discussing PYQ na. So I will not teach entire topic, that will become very time consuming na. But just for understanding, since you are asking na, in force vibration, if in general case spring parallel to spring one damper is attached, with this mass is attached, and in this some harmonic force is acting F0 sin omega t, it is C, it is K. So we consider na steady state vibration in force vibration. Steady state vibration means actually here if you find the equation of x na, it will be, if you solve mathematically, it will be CF plus PI. But in steady state vibration, we neglect the effect of complementary function, that is CF. Now don't go in too much detail. So whenever I am taking in force vibration x equal to PI, that is known as steady state vibration. And if force is like this F0 sin omega t na, so the steady state vibration equations come like this. It will have simple harmonic function which is capital X sin omega t. See, if force is sin omega t na, here it will be capital X sin omega t minus theta. Means what I am trying to say, if the forcing frequency is omega, the forcing frequency of steady state vibration is also omega. Okay, but the amplitude of steady state vibration I am denoting as capital X, and here some phase difference will come. Like here if sin omega t is coming, it will be sin omega t minus theta. Like here if it is cos omega t, it will be cos omega t minus theta. If it is here it is sin omega t plus pi by 2, it will be sin omega t plus pi by 2 minus theta. Theta is known as phase difference. Now here the formula to calculate capital X, that is amplitude of steady state vibration, is F0 by K upon square root of 1 minus R square whole square plus 2 zeta R whole square, where F0 is the amplitude of force, K is the stiffness of spring, R is known as frequency ratio, which is omega by omega n. Now whenever R is 1, that is known as resonance frequency. Okay, yes, and zeta is damping factor, you already know, whose formula is C upon 2 root over Km or C upon 2m omega n for general case. Okay, now here remember one more thing, this ratio X by F0 by K, if you bring this F0 K by kilowatt, it is known as magnification factor. Sometimes examiner will refer this as amplitude ratio also, but it is known as magnification factor. Definitely its formula will be this 1 upon root over 1 minus R square whole square plus 2 zeta R whole square. Detail of this you have to watch the YouTube video, na? Yes, and here the formula to calculate this phase difference theta is tan theta is equal to 2 zeta R upon 1 minus R square. Yes. Now for this question, examiner has given when it is resonance, means R equal to 1, capital X is 1 centimeter. I use that, and here if you put R equal to 1, after simplification this term is coming, I calculated the expression of F0 by K. Now when omega is 0.5 times omega n, means R is equal to 0.5, then capital X is this. So I put it this in this equation. From this also I calculated F0 by K. Since both are representing F0 by K, I equated them. Now it is calculation, we have calculated the value of zeta. Harry. Yes. Now here amplitude ratio means simply think magnification factor is given, it is 2.5. At resonance means R is equal to 1, you have to calculate zeta. Okay. Now we know the formula to calculate magnification factor, it is nothing but capital X upon F0 by K. It is 1 upon square root of 1 minus R square whole square plus 2 zeta R whole square. But right now it is given at resonance means R equal to 1. Now here we put R equal to 1 now, it will become R equal to 1, it will become 0, R equal to 1. So it will 2 zeta whole square. If you bring outside root, it is 1 upon 2 zeta. Now magnification factor is 2.5. That is equal to 1 upon 2 zeta. So from this I can calculate zeta. How much it is coming? 1 divided by 2.5 divided by 2. Is it coming 0.2? So for this question, damping ratio or damping factor is 0.2. Okay. Now I am discussing some question related to double degree of freedom system. Okay. In double degree of freedom system, questions comes related to the calculation of natural frequency. Sometime question will ask mode shape. What is mode shape? That I also will discuss. Good. But again, I will directly solve the question. Briefly, I will explain. But for detailed explanation, you can watch YouTube video also. So now, you will see my YouTube series for vibration in this channel. Na? I discuss double degree of freedom vibratory system also. Okay. So see. Consider the system. Actually, na, it is common data question. Same question I had taken for this same diagram. You will see whether you see this diagram or this diagram is same. Okay. So that's why solution of this question and this question I will do simultaneously. Okay. So consider the spring mass system shown in figure. This system has 2 degrees of freedom representing the motion of two masses. Very good. Now, what is the coupling of this system? This is first part, static, dynamic, or both static and dynamic, or no coupling. Second part, what will be the two natural frequency of this system? Plus, minus. Now, so one natural frequency will get by taking minus, other will get by plus. And question is same. So this both question figure is same. Na? Now, whenever this type of question is coming, so first we will derive the governing equation of vibration. Okay, one governing equation I will get from the FBD of this first mass. So this mass I am representing as mass 1, which mass is m, that is different thing. Second equation I will get from the FBD of mass 2 from this FBD of this mass. Okay, mass 2, actual value of mass 2, that is m2 is 3m, that is different thing. Okay, now it is a 2 degree of freedom system, because here suppose the displacement of mass 1 from mean position is x1. Okay, this side, here displacement of mass 2 from mean position is x2. So see, without knowing the value of x1 and x2, now I cannot decide what will be the deflection of all spring. Like if I know x1, the deflection of this spring will be x1 because it is between x1 and fixed. If it is x2, displacement of this spring is also x2 because it is between x2 and fixed. But what will be the, see, so see, to calculate, say the deflection of this spring, I require x2. To calculate the deflection of this spring, I require x1, means I require both x1 and x2. Means degree of freedom of the system is 2. And to tell what will be the deflection of this spring, I require both x1 and x2 because it is between x1 and x2. Like if x1 is more, deflection of this middle spring will be x1 minus x2. If x2 is more, deflection of this middle spring will be x2 minus x1. So I require both x1 and x2, means the degree of freedom of this system is 2, and if degree of freedom of this system is 2, it will have 2 natural frequency. I discussed in class in very detail, even in YouTube series also. But how we can find first governing equation? Okay, governing equation. So see, for that now we will draw the FBD of mass 1 separately, FBD of mass 2 separately. Here in FBD of mass 1, this spring is that is, suppose this spring is 1, it is 2, it is 3. Okay, so I am cutting spring 1 from this location, I am cutting spring 2 from this location. Similarly, to draw the FBD of mass 2, I am cutting this spring from this location, this spring 3 from this location. So FBD will be like this, FBD of mass 1. Mass is m, that is different thing. Here 2 spring is coming, spring 1 which I cutted from this location. It is spring 2 which I cutted from this location. At the location from where we have cutted the spring, okay, internal spring force will come. Very good. Yes. Similarly, I am drawing the FBD of mass 2. Here this spring is that is, which is spring 2 which I cutted from this location. This spring is that is, which is spring 3 I cutted from this location. And the value of m2 is 3m, na? That is different thing. Okay. Displacement of mass 1 from mean position is x1, it is x2. Okay. Now first I will apply spring force. For that, see the deflection of any spring, and that is by that I mean spring is elongating or contracting. Because as per this direction, if a spring is elongating, spring force will be tensile. If it is contracting, spring force will be compressive. Okay. So see. Okay. See, right now displacement of this mass from mean position is x1 this side. So this spring is between x1 and fixed. So can I say displacement of this spring will also be x1? And since it is going like this, spring 1 will elongate. So can I say here deflection of spring 1 is x1, and by this amount it is elongating. Okay. So can I say spring force of spring 1 will be kx1, and it is elongating, means force is tensile. So at this point first draw, because from here I cut a spring 1, na? Draw such arrow which will elongate this portion because it is tensile. For that I need to draw arrow like this, and the value of force is kx1. Okay. Now what is the deflection of spring 2? So you can see spring 2 is coming between x1 and x2. Now if x1 is more, you will say spring 2 deflection will be x1 minus x2. Good. But if it is x1 minus x2, na, so by that amount, na, this spring will contract, because in that case, can I say x1 is dominating, and as per this direction of x1, spring will elongate, sorry, contract, and as per this direction of x2, spring will elongate. So since x1 is dominating, overall it will contract. But if x2 is more, then deflection of this middle spring will be x2 minus x1, but by that amount, spring will elongate because now x2 is dominating. But here we are doing the derivation, so here both are possible. So see, during derivation, it is your will. If you want to assume x2 greater than x1, you can assume. If you want to assume x1 greater than x2, you can assume. But see, after taking this assumption, what your final equation will come, na, that is valid for all combination of x, whether x1 is more than x2, whether x2 is more than x1. Why? Because see, When I am assuming x2 greater than x1, so I will take the deflection of this spring x2 minus x1. And by this amount, now x2 is dominating, as per this direction, it will elongate. So we will say as per the, by this amount, spring will elongate. Okay. Because right now I have done the derivation by assuming this. But whatever final equation will come now, that is valid for this case also. And when x1 is more, for that case also it is valid. Because when x1 is more, automatically it will come negative. Okay, negative. And in that case, actually it will compress. But when I am saying it is elongating, but automatically if it is coming negative, means actually is opposite to that. Means it automatically, mathematically is covering that error. Error means if x2 is more, it will elongate, so it will come positive. Good. If x2 is less, it should contract. So automatically it will come negative. When I assumed elongation, automatically it is coming negative. Means actually it is taking that as compression. So whatever final equation will come now, that is valid for all combination of x. Okay, but due for derivation, take any assumption. So since I assumed x2 is more, net deflection x2 minus x1, and as per this it is elongating. So can I say spring force of spring 2 is k in bracket x2 minus x1, and right now as per this effect, its nature is tensile. So this is the spring 2 I have cut it from this location in this ABD. So first draw as tensile like this, because it is trying to elongate this, and spring force is k in bracket x2 minus x1. Because stiffness of spring 2 is k na. It is also spring 2 ABD, which I cut it from this location. So draw such a row which will try to elongate this portion, because this I have drawn in this ABD. For that I need to draw a row like this, and spring force is stiffness k in bracket x2 minus x1. Clear? Now what about spring 3 spring force? Its stiffness is k. Now it is between x2 and fixed, so deflection of spring 3 will be x2. And by this amount, if x2 is like this, it will contract. So by this amount, can I say it is getting contract? So spring force of spring 3 will be kx2 compression. So first, this is the ABD of spring 3. So at this point, draw such a row which will contract this portion. For that, I need to draw a row like this. Now value is kx2. So spring force part completed. Now inertia force will apply. So see, inertia force for any mass is always mass into acceleration. Direction of acceleration will be opposite to the, direction of this inertia force will always be opposite to the acceleration. So see, the mass of mass 1 is m. Now its displacement from mean position is x1. So can I say acceleration velocity will be x1 dot, acceleration will be x1 double dot, yes or no? And direction of x1 double dot will be same as x1 if you are calculating by differentiation. Okay. So can I say inertia force for mass 1 will be mass m, acceleration x1 double dot. So inertia force will be m x1 double dot. It is opposite to x1 double dot. Right now x1 double dot this side, so it will be this side. Okay. Similarly, inertia for this mass of this mass is 3m. Its displacement is x2. So can I say acceleration will be x2 double dot? I am directly writing. So inertia force will be 3m x2 double dot. Direction opposite to x2 double dot. x2 double dot direction mathematically it will be same as x2. So x2 double dot this side. So inertia force will be opposite to this, means it will be this side. Now after applying inertia force, you can assume that individual ABD in equilibrium. So this is the ABD of mass 1. This is the ABD of mass 1 too. Consider separately. Na? So in the ABD of mass m1, if I will take summation of force in x direction 0, so I will get first governing equation from the ABD of mass 1. While using this, suppose I am adding this side force, so we'll subtract this side force. Okay. Now, or what I am doing, most of the force are coming this side. So suppose I am adding, it doesn't matter whether you are adding this or subtracting this, or adding this or subtracting this. So my habit is now, see, the inertia force is in this direction. So generally I add this direction and subtract this direction, because most of the force are coming in this direction. But final answer will not change. Okay. So right now I am adding this side, suppose I am subtracting this side. So mx1 double dot this side, which I am adding. Okay. kx1 this side, which I am adding, plus kx1. kx2 minus x1 is this side, which I am subtracting. So minus k in bracket x2 minus. If I am doing any calculation, please correct me. If you want to simplify this, it will be mx1 double dot plus kx1 minus kx2 minus plus kx1 equal to 0. Now I am writing the equation in standard form. Like first I am writing x1 double dot term, mx1 double dot. If any x2 double dot term will come, then I will write x2 double dot term. But right now no x2 double dot term is coming. Now write first x1 term. So this is kx1 plus kx1, it is 2kx1. Now write x2 term, so it is minus kx2. It is equal to 0. So this is the governing equation which I got from ABD of mass 1. Okay. Similarly, in ABD of mass M2 will take summation of force in x direction and equate with 0. Yes. Now again, while using this, suppose I am adding this side for subtracting this side. So 3mx2 double dot is this side, which I am adding. K in bracket x2 minus x2 1 is this side, which I am adding. So plus k in bracket x2 minus x1. Now this kx2 is also this side, which I am adding. So plus kx2. Now it is equal to 0. It is coming. No x1 double dot is coming. So now write x2 3m x2 double dot plus kx2 minus kx1 plus kx2 equal to 0. So first I am writing x1 double dot term, that is not coming. So now write x2 double dot term. It is 3m x2 double dot plus. Now write first x1 term. So it is minus kx1. Now write x2 term. So plus kx2, it is plus 2kx2. It is equal to 0. Yes. After then you can do the go for the calculation of natural frequency. But since here examiner asking coupling also now. So whenever examiner is asking coupling, we can write this two governing equation 1 and 2 in a matrix form. In matrix form, how we write now? See, like for general single degree of freedom system, equation of vibration is like this: mx double dot plus kx equal to 0. So in matrix form for double degree of freedom system, it will be like this: mass matrix into x double dot. X double dot means here one matrix will come of 1 by 2 order, in which x1 double dot and x2 double dot will come, because in acceleration 2 term is coming, na, x1 double dot, x2 double dot, plus stiffness matrix. This is stiffness matrix. I will write or explain how to write stiffness matrix. Into x, in x it will be x1 by x2, that is equal to 0 matrix, like this. Now see, in the mass matrix now, what this force mass and stiffness matrix for 2 by 2 for 2 degree of freedom is always 2 by 2 order. So see what this first element in first row is representing now. See, this first element is representing the coefficient of x1 double dot in equation 1, which we got from the FBD of mass 1. Similarly, it is representing the coefficient of x2 double dot in equation 1. Similarly, here this term represent the coefficient which we are getting from equation 2. Like first element represent the coefficient of x1 double dot in equation 1, sorry, equation 2. And this represent the coefficient of x2 double dot in equation 2. Same is valid here, only difference, instead of acceleration we are taking the coefficient of displacement. So for element in first row represents coefficient which we are getting from equation 1. Second row represent the coefficient which we are getting from equation 2, that is from FBD of mass 2. Like this represents the coefficient of x1 in equation 1, it represents the coefficient of x2 in equation 1. Similarly, it represents the coefficient of x1 again, but in equation 2. It represents the coefficient of x2 again, but in equation 2. Okay, so like, see, it is coefficient of x1 double dot in equation 1 and coefficient of x2 double dot in equation 1. So right now if you see now, in equation 1, which I am getting from FBD of mass 1, coefficient of x1 double dot is m, but no x2 double dot is coming, term is coming. So can I say coefficient of x2 double dot is 0? So in equation 1, coefficient of x1 double dot m, coefficient of x2 double dot 0. Now, same coefficient in equation 2. So see, in equation 2, no x1 double dot in term is coming. So can I say coefficient of x1 double dot is 0 and coefficient of x2 double dot is 3m. So in equation 2, coefficient of x1 double dot is 0 and coefficient of x2 double dot is 3m. Okay. Now, what about stiffness matrix? So first see, it is coefficient of x1 in equation 1, coefficient of x2 in equation 1. So in equation 1, coefficient of x1 is 2k and coefficient of x2 is minus k. So coefficient of x1 is 2k and coefficient of x2 is minus k. Similarly, in equation 2, coefficient of x1 is minus k and coefficient of x2 is 2k. So in equation 2, coefficient of x1 is minus k, coefficient of x2 is 2k. Now, what is the meaning? I am not going in detail because it's just a PYQ series. Na? So see, in mass matrix, na, if non-diagonal term is, if this term is non-zero, right now it is 0. I am not explaining for this question. Non-diagonal term is non-zero, then we say that system is having dynamic coupling. And if it is 0, then we say there is no dynamic coupling, because inertia force is dynamic force. Similarly, if a stiffness matrix, if non-diagonal term is non-zero, means it is having static coupling. If it is 0, then there is no static coupling. Okay. So right now it is having dynamic coupling or not. So actually here non-diagonal term is 0, and since it is 0, means can I say first conclusion is there is no dynamic coupling. Second, since stiffness matrix non-zero term are non-zero actually, so it is having static coupling. So with respect to coupling, it is having only static coupling because it is having no dynamic coupling. This was first part. So it is having only static coupling. So A is correct. The no dynamic coupling, so B is incorrect. C is also incorrect, and no coupling is also correct, incorrect because it is having static coupling. So for this question, option A is correct. Clear? Yes. Now how will calculate the natural frequency? Two natural frequency, na? So see, if you want to calculate natural frequency, then you need not write this in matrix form. Simply na write the equation which we are getting, equation 1 which we are getting from FBD of mass 1, which we have written. It is mx1 double dot plus plus 2kx1 minus kx2. If I am doing mistake in putting the, correct me, plus 2kx1 minus kx2. This is equal to 0. Similarly, write the equation which we got from FBD of mass 2. It was 3mx2 double dot minus, I think, kx1 plus 2kx2. Please correct me if I am doing in any incorrect. Yes, equal to 0. Now, 2 degree of freedom system na, it means it will have two natural frequency. Out of those two natural frequency na, the smaller natural frequency is generally I am denoting as omega 1, and larger natural frequency I am denoting as omega 2. This smaller natural frequency is also known as natural frequency corresponds to first degree of freedom system, and larger natural frequency is also known as natural frequency with second degree of freedom system. Now when system will vibrate na, it depends upon the how we are providing initial displacement. Okay, question related to that also will come later when you understand the concept of mode shape, but right now we have to do nothing to with mode shape. So whenever system is vibrating now, that depends upon the initial displacement which we are giving in the both the mass. Based on that, either entire system will only vibrate with frequency omega 1, means in the equation of x1 and x2 only one harmonic term will come which frequency is omega 1, or it will vibrate only with frequency omega 2, mean the equation of x1 and x2 only one harmonic term will come which frequency will be omega 2, or it might be possible that it will vibrate with the combination of omega 1 omega 2. Combination means in the equation of x1 and x2 actually two harmonic term will come in which the frequency of one term will be omega 1 and frequency of other term will be omega 2. But to write these equations, first I need to calculate omega 1 and omega 2. So whenever you are calculating omega 1 and omega 2, right now our objective is to only to calculate omega 1 and omega 2. Lesser natural frequency is omega 1, larger is omega 2. So we are assuming right now at one time system is only vibrating with single frequency, whether it is omega 1 or omega 2. Suppose that I am denoting as omega, and I will get after calculation automatically two value of omega. One is omega 1, other is omega 2. Means can I say, okay, x1 and x2 is vibrating only with single frequency omega. So x1 x2 equation both will be, in both equation only one harmonic term will come which frequency will be omega. Now general representation of harmonic term is capital X sine omega t plus phi. It is general representation. Na? So suppose the amplitude of mass 1 I am representing as capital X1. So it will be capital X1 harmonic term, that is sine omega t plus phi. Similarly, X2 will be capital X2. Suppose amplitude of mass 2 in this case is capital X2 sine term. Sine term is right like this, sine omega t plus phi. Okay. Yes. Because we are assuming it is vibrating only with frequency omega. Now if we are taking x1 x2 this now, so here in equation 1 and 2 x1 x2 are coming, but along with this x1 double dot x2 double dot term is also coming. So now calculate x1 double dot. X1 double dot now I will discuss a trick. Even when you are calculating frequency now, you need not to write this entire things. Just you can keep this in your mind. See here capital X1 capital X2 is coming. Refer this as sine term. Now if you will differentiate this with respect to time two times now, so you will differentiate one time, it will be capital X1 omega and differentiation of sine is cos. Then again if you will differentiate, it will become capital X1 omega square and differentiation after sine it has become cos, and differentiation of cos is minus sine. So what I am trying to say, if you will differentiate mathematically this equation with respect to time two times now, it will become minus capital X1 omega square sine omega t plus phi. You can check after differentiation this will come. Like it will calculate x2 dot double dot now, it will be minus capital x2, sorry omega square it is, omega square sine omega t term plus phi. Sine term I am referring as. So now you can refer like this. See, when I will do replacement in equation 1 and 2 now, by assuming it is vibrating only with single frequency omega. So x1 will be capital X1 sine term, x2 will be capital X2 sine term. Then you can keep this in your mind. Then x1 double dot will be minus capital X1 omega square. Just remember this sine term. For sine term, you need not try to entire this. Just in your mind, say sine term. x2 double dot will be minus capital X2 omega square sine term. So if we do this replacement in equation 1 now, what will happen? Equation 1, I am putting in equation 1. Now you can directly put, even you need not to write this, x1 by capital X1 sine term, x2 by capital X2 sine term, x1 double dot by minus capital X1 omega square sine term, x2 double dot is not coming. But when you will put now, in each term sine omega t plus phi will come. So I can take sine omega t plus phi common, and common part will come this side, it will merge with 0, it will become 0. So even you need not to write sine term. So ultimately now you can directly write like this. Equation 1 will become, equation 1 is m x1 double dot. So I am replacing x1 double dot by minus, just remember this, capital X1 omega square sine term. Sine term will go other side by coming common, it will become 0. So that's why I am not writing. Okay, plus 2k x1 plus 2k, and x1 is capital X1 sine term is coming common, it will going other side, it becoming 0. Minus kx2, and x2 is capital X2 sine term equal to 0. So suppose this I am referring as equation 3. Okay, see, or 0. From this either find x1 by x2 or capital X2 by x1. So suppose I am finding capital X2 by x1. You can find now. It will be minus m capital X1. I am taking common omega square. Here also capital X1 is coming, plus 2k into capital X1. This minus kx2 will come this side. It will become plus kx2. From this it will calculate capital X2 by x1. X2 by x1. It will be minus m omega square plus 2k divided by k. Clear? Suppose this is equation 3. Yes. Do this replacement in equation 2 also. It will become, see, 3m x2 double dot. So I'm doing, you can do in your mind, x2 double dot by minus capital X2 omega square sine term. Sine term will come common, it will go other side, it will become 0. Minus kx1. So minus k. X1 is capital X1 sine term will go other side, it will become 0 after coming common. Plus 2kx2, and x2 is capital X2 sine term, that is equal to 0. From this also find capital X2 by x1. So it will be minus 3m omega square, capital X2 I am taking common, capital X2 is coming also here, na? No, not here, here. So plus 2k into capital X2. Now this part is remaining minus kx1, it will go other side, it will become plus kx1. Okay. From this also calculate capital X2 by x1. So can I say capital X2 by x1 will be k upon minus 3m omega square plus 2k. Now, very simple, equation 4. Now you can see both equation 3 and 4 are representing capital X2 by x1. So I can equate them because both are representing capital X2 by x1. Just, this is final equation. So 3 is minus m omega square plus k, sorry, plus 2k upon k, that is equal to, equation 4 is k upon minus 3m omega square plus 2k. Now, if you solve this now, you will get two value of omega that represent two natural frequency. Lesser is first natural frequency, larger value is known as second natural frequency. Okay. Now, but if you will do calculation here, if you multiply this term, omega to the power 4 will come. So calculation will be little bit complicated. So during calculation, what I am doing, omega square, I am replacing omega square by lambda, and I will get two value of lambda. Okay. Now, lesser value of lambda is omega 1 square because lesser natural frequency is omega 1. Larger value of lambda is omega 2 square. Okay, and after calculating omega 1 square, omega 2 square, you can calculate omega 1 and omega 2 also. So just replace omega square by lambda. So it will become minus m lambda plus 2k. This part will come this side, it will become minus 3m lambda plus 2k, that is equal to k into k square. Now expand this. So minus minus, it is plus m into 3m is 3m square lambda square. Now minus plus minus 2km lambda plus minus minus 3 to just 6 km lambda plus into plus 2 to just 4k square. K square will come this side, it will become minus k square equal to 0. So it is coming 3m square lambda square minus 2k minus 6k minus 8km lambda plus 4 minus 1 3k square equal to 0. You can see it is double order polynomial. And to find the root of this equation, okay, value of lambda, the formula you can use, if equation is like this, ax square plus bx plus c equal to 0, x will be minus b plus minus root over b square minus 4ac upon 2a. Just use that. So coefficient of lambda is b, which is minus 8 km. So it is minus of minus 8 km plus minus root over b square means minus 8 km whole square minus 4ac is the coefficient of lambda square, which is 3m square, into c is this constant part, which is 3k square, divided by twice of a, that is twice of 3m square. Now what will happen from above, now automatically always km term will come common, because here km is coming, here you will see it is km whole square. If bring outside root, again km will come common. Here it is k square m square means again km whole square. If you bring outside root, km will come, and overall km is coming common. So from above take km outside, from below it is 3 to just 6m square, yes or no? In bracket it is minus minus plus 8 km I have taken common, plus minus inside root it will be minus 8 square, minus 2 square plus 8 is just 64. Km whole square I have taken common, come to outside root, it has become km, and km I have written this side. So from inside root we have taken km whole square already common na. So write the term apart from km whole square inside root. So here minus, it is 4 3 are 12, 12 3 are 36 km whole square, which I have taken common. So this is coming, this is okay. So I am getting 2 LO lambda, 1 m will get cancelled, so it is k by m inside bracket. Okay, now calculation I am doing direct calculation, because this is mathematics. Root 64 minus 36 is 2 root 7. So actually it is 8 plus minus 2 root 7 divided by 6. You can also write like this, k by m. Okay, 8, 2 I can come from common, 2 divided by 6 is 1 by 3 na? So it will become, here 4 will remain, plus minus root 7 divided by 3, and lambda is nothing but omega square. So can I say omega is root over this, means it is root k by m root 4 plus minus root 7 divided by 3, because right now option is given like this. Instead of the examiner, if examiner is asking what is first or lesser natural frequency, the frequency which is coming by taking minus sign, means it is 4 minus root 7 divided by 3 into this. What is larger natural frequency? 4 plus root 7 divided by 3 into this. But right now option are given like this. So 2 natural frequency of this system is coming. Okay, root k by m, then is after that square root of 4 plus minus root 7 divided by 3, matching with which option? Option 3. So for this question, option C is correct. So like this you can do calculation. Okay, now I am just discussing one more question, then I will not discuss similar type of question. Here again we have to calculate the 2 natural frequency of this system. One, okay, again it is 2 degree of freedom system na. So displacement of this mass from mean position is x1, it is m1. Displacement of this mass from mean position is x2. Stiffness, only one spring is there, its stiffness is k. Now suppose I am cutting this spring from this location, cutting this spring from this location. Suppose this is spring 1. So we will draw the FBD of mass 1. It will be like this. With mass 1, this spring is attached, whose stiffness is k. This is spring 1 na. With mass 2, again this same spring is attached, whose stiffness is k. But I have cut it from this location. It is x1, it is x2. Now to draw FBD, either assume x2 is more than x1 or x1 more than x2. So suppose I am assuming x2 is more than x1. Then deflection of this is, it is between x1 and x2. Since x2 is I assumed more, so it will be x2 minus x1. And as per x2 direction, it is elongating. So by this amount, it will elongate. Okay. So can I say spring force of this spring will be k in bracket x2 minus x1, and right now my assumption is tensile. So at this point, I have cut it from this location. First draw tensile force. Draw as such a which will elongate this like this, and force is k in bracket x2 minus x1. It is also representing the FBD of spring 1, which I have cut it from this location. So first draw spring force as tensile. For that, draw such a which will elongate this like this. Force is k in bracket x2 minus x1. Very simple. Yes. Now inertia force. So mass 1, mass 1 is mass 1. Its displacement is x1. So acceleration will be x1 double dot. So inertia force will be m1 x1 double dot. Direction opposite to x1 double dot. x1 double dot is this side, so it will be this side. Similarly, this mass is m2. Its displacement is x2. So acceleration will be x2 double dot. So inertia force m2 x2 double dot. Direction opposite to x2 double dot. x2 double this side, so it will be this side. Okay. So this is FBD of mass 1. It is FBD of mass 2. After applying inertia force, we can consider individual FBD are in equilibrium. So if you will use the FBD of mass 1, in that FBD use summation of force in x direction and equate with 0 after applying inertia force. Now, suppose I am adding this side force, then subtract this side force. So x1 double dot is this side which I am adding. This is spring force this side which I am subtracting. It is plus k in bracket x2 minus x1. Apart from this, no other force is coming. Equate with 0. So it is like m1 x1 double dot plus k x2 minus k x1, that is equal to 0. If you want, you can write like this: m1, if you want to write standard force, minus k x1 plus k x2. It's not necessary if you want to write like this. Suppose this is equation 1. Okay. Similarly, from FBD of mass 2, use summation of force in x direction 0. Okay, good. Now, while using this, so again, suppose I am adding this side force, then subtracting this side. So m2 x2 double dot is this side which I am adding. Okay. Plus now, see, this spring force is also this side which I am adding. So it is plus k in bracket x2 minus x1. If you expand this, equate with 0. It is m2 x2 double dot plus kx2 minus kx1. Now, if you want to write x1 term first, you can write it your will, but not necessary. It is equation 2. Now, what I will do? I will replace x1 by capital X1 sin term. I am not writing. And I will replace x2 by capital X2 sin term. Sin term is sin omega t plus phi. Then x1 double dot will be minus capital X1 omega square sin term. Keep in your mind. x2 double dot will be minus capital x2 omega square sin term. But when you put na, automatically sin term will come common. It will go other side. It will become 0. So if we do this replacement in equation 1, can I say equation 1 will become m1 x1 double dot. I am replacing x1 double dot by minus capital X1 omega square sin term. Sin term is coming common, going other side, it will become 0. Minus kx1. So minus kx1. X1 is capital X1 sin term. Sin term is going common, going other side, it will become 0. Plus kx2. So plus kx2. X2 is capital X2 sin term. Sin term is coming common, going other side, it is becoming 0. Now from this, calculate capital X2 by X1. So it is minus m1 omega square capital X1 I am taking common. Here also capital X1 is coming. So minus k. I think I had done some mistake. This is equation 1. Yes, I had done mistake. See, I added this side force now m1 x1 double dot. So I need to subtract this side force. So actually kx2 minus x1 is this side which I am subtracting. By mistake here I again plus. This is calculation error. Please correct this. See, if I added this side force, I need to subtract this side force. So this force I am subtracting. So minus. Next one, it is minus kx2 plus kx1. We are writing x1 term first, plus kx1 minus kx2 equal to 0. Yes, this is equation 1. Equation 2 is correct because both this side, so both will get added. Yes, but equation 1 there was mistake. Equation 1 we have replaced x1 double dot by minus capital X1 omega square. So minus m x1 omega square will, capital X1 will, omega square will remain. Now it is plus kx1. So plus kx1 x1 by capital X1 sin term minus kx2. So it is actually minus k x2 by capital X2 sin term. Sin term is coming common, going other side, it will become 0. Now from this, calculate capital X2 by x1. It is minus m1 omega square capital X1 I am taking common. Here also capital X1 is coming, so plus k. Here capital X1 is not coming, so don't take this capital X1. Now shift this part this side, it will become plus kx2. From this, calculate capital X2 by capital X1. It is coming minus m1 omega square plus k upon k. Suppose this is equation 3. Again, do same replacement in equation 2. Equation 2. It is m2 x2 double dot. So m2 x2 double dot replaced by minus capital X2 omega square sin term. Sin term will come common. Plus kx2. Plus kx2. x2 is capital X2 sin term minus kx1. And x1 is capital X1 sin term. Sin term is coming common. Going other side is becoming 0. Now it will be minus m2 omega square capital X2 I am taking common. Here also capital X2 is coming. So plus k into capital X2. Here capital X2 is not coming. So shift other side. It will become plus k capital X1. From this, calculate capital X2 by x1. It is coming k upon minus m2 omega square plus k. Suppose this is equation 3. Sorry, 4 na? 3 already. Now see, both equation 3 and 4 is representing x2 by x1. So I can equate them. Yes, this is the final equation. From equation 3 I am getting minus m1 omega square plus k upon minus k. Okay. From equation 4, sorry, it is plus k, sorry, plus k. From equation 4, I am getting k upon minus m2 omega square plus k. Okay. And just replace omega square by lambda. You will get 2 value of lambda, means 2 value of omega square. So it is minus m lambda plus k into, sorry, minus m1 lambda. This what? Minus m2 lambda plus k into k square is, that is k square. Now it will be minus minus plus m1 m2 lambda square. Yes. After that, minus m1 m2 lambda square. That minus plus minus k m1 lambda plus minus minus k m2 lambda plus into plus k square minus k square equal to 0. Here it is becoming simple. This part is getting cancelled. So it is coming m1 m2 lambda square minus k. I say it is k in bracket m1 plus m2 into lambda. We'll take minus k lambda common. It will be m1 plus m2 equal to 0. Now here you don't require equations. You can directly solve because I can take 1 lambda common. So it will be lambda in bracket m1 m2 lambda minus k in bracket m1 plus m2. So how I will calculate lambda, 2 value of lambda? This will be 0 when this part is 0. So from this I will get 1 value of lambda equal to 0. Okay. Now if you equate this part 0, you will get other value of lambda. It will come k in bracket m1 plus m2. I am doing direct calculation upon m1 m2. This is mathematics. Okay. This lesser value of lambda is omega 1 square. Omega 1 square is 0. Means omega 1 is 0. So here first natural frequency is 0. Larger value of lambda means omega 2 square. It is larger natural frequency or second natural frequency. It is k in bracket m1 plus m2 upon m1 plus m2. So omega 2 will be root over this. This is root over k in bracket m1 plus m2 upon m1 plus m2. Okay. So this is the two natural frequency. One is 0. Another one is this. Matching with which option? First is 0. Another one is root k in bracket m1 plus m2 upon m1 plus m2. Check the answer. Yes. So it is matching with option A. So for this question, the correct answer is option A. Okay. Now this is your homework because again it is similar type of questions. Just do the derivation. Now examiner asking largest natural frequency means you have to calculate omega 2. You will get 2 omega, omega 1, omega 2. So take larger value. Where it is? Oh, this is typing error. Yes, correct that. M1, M2 na. There indirectly examiner asking omega 2. Now sometime na, because it's little bit time consuming na, so it might be possible to simplify this. Examiner will give the equation directly. Then examiner asking here, if the larger natural frequency means second natural frequency is alpha root k by m, what is the value of alpha? So here you have to calculate second natural frequency. Now it is more easy na because equation is already given. So see, first equation is m x1 double dot plus 2k x1 minus k x2 equal to 0. Yes. Second equation is m x2 double dot minus k x1 plus 2k x2 equal to, if I am doing any calculation, put error or error in putting, please correct this. So again, what we'll do in both the equation, we'll replace x1 by capital X1 sin term, x2 by capital X2 sin term, then x1 double dot by minus capital X1 omega square sin term, x2 double dot by minus capital X2 omega square sin term. So equation 1 will become m x1 double dot by minus capital X1 omega square sin term. Sin term is coming common plus 2k x1, x1 is capital X1 sin term minus k x2. So minus k x2, x2 is capital X2 sin term is coming common, it is coming, going other side, it became 0. From this again calculate capital X2 by x1, so it is minus m omega square capital X1 I am taking common, here also capital X1 is coming plus 2k capital X1, that is minus k x2, it will go other side plus k x2. So from this we will calculate x2 by x1, it is coming minus m omega square plus 2k upon k. Suppose this is equation 3. Okay. Do same replacement in equation 4. It will become m x2 double dot. So m x2 double dot is minus capital X2 omega square sine term minus k x1 minus k x1 is capital X1 sine term plus 2k x2 plus 2k x2. x2 is capital X2 sine term, that is equal to 0. From this minus m omega square capital X2 I am taking common. So capital X2 is also coming here, not here. So plus 2k capital X2 minus kx1, it will go other side, it will become plus kx1. So from this again find capital X2 by x1, it is coming minus m omega square plus 2k divided by k. Suppose this is equation 4. Equation 4. Okay. Since both equation 3 and 4 are representing x2 by x1, just equate them. Okay. So as per equation 3, it is minus m omega square plus 2k upon k. As per equation 4, it is k upon minus m omega square plus 2k, and replace omega square by lambda. So it will be minus m lambda plus 2k into minus m lambda plus 2k, that is equal to k square. Now minus minus plus m square lambda square, then minus plus minus 2 km lambda plus minus minus 2 km lambda plus 4k square minus k square is equal to 0. It will be m square lambda square minus 4 km lambda 4 minus 1 plus 3k square, that is equal to 0. From this I can calculate 2 value of lambda means 2 value of omega square. It will be minus b is minus 4 km. So minus of minus 4 km plus minus root over b square means minus 4 km whole square minus 4 ac a lambda square coefficient which is m square. So minus 4 m square, c is this part which is 3k square. Below said twice of a is the coefficient of lambda square which is m square. Now above said always km will come common. Below said it is m square. So inside it will be minus minus plus 4 km I have taken common plus minus. Means can I say inside root we have taken km whole square common. So km whole square I have taken common. So apart from this here minus 4 square is coming. Minus square is plus 4 4 is 16 minus. Now it is 4 3 is 12 km whole square which I have taken common. Na? Okay. Divide by this 2. Okay. So 1 m will get cancelled. It is k by m. So it is coming 4 plus minus root 16 minus 12 root 4 is 2 divided by 2. So now what will happen? If you will take lesser value of minus sign, you will get lesser value of lambda. It is coming 4 minus 2 2 divided by 2 is 1. So it is coming k by m means it is omega 1 square. So can I say omega 1 is root k by m, which is smaller or first natural frequency. Well, take plus and I will get larger value of lambda, which is 4 plus 2 6 divided by 2 is 3. So 3k by m. It is omega 2 square means okay. So omega 2 is root k by m. So here larger natural frequency is root 3k by m. Now in examiner is saying right now larger natural frequency is alpha root k by m. Na? So examiner is saying larger natural frequency, that is omega 2 is alpha root k by m, and after calculation I got it is root 3k by m. So from this you can calculate alpha. Can I say alpha is root 3? Root 3 means 1.732. So for this question the value of alpha is coming 1.732. Very good, Harry. So this is correct answer for this question. Clear? Now here I am discussing some concept related to mode shape. See, first of all, what is the mode shape? Then we'll discuss significance. So see, here this question is coming now. It is very easy question because here now initial displacement is already given. Okay, but sometime now it might be possible examiner is giving complete diagram and examiner will ask mode shape. Okay, what is this I am explaining? So suppose first for this question I am discussing. See, in this question in last question, in this question examiner not asking mode shape, but to explain I am explaining. You will see the expression of x2 by x1. Okay, ultimately the expression of x2 by x1, whether you take equation 3, because both are representing x2 by x1. So as per equation 3 it is minus m omega square plus 2k upon k. Similarly, write any one equation. Similarly, as per equation 4, it is as per equation 4. As per see here, I think it is my mistake. Here I have written correct. Here x2 by x1 is coming k upon minus m omega square plus 2k. Sorry. So as per equation 3, it is coming this. As per equation 4, it is coming k upon minus m omega square plus 2k. But both are representing x2 by x1. Now see, if you want to calculate first mode shape, okay, what is the significance of this? I will explain later. But what is the meaning of first mode shape? For that, now we'll calculate x2 by x1 corresponds to first natural frequency. First calculate this. Okay, so what I will do in this equation, suppose it is equation 5, if we put omega equal to omega 1, right now omega 1 is root k by m, but in formula omega square is coming. So can I say omega square will be k by m? You will get x2 by x1 corresponds to first natural frequency, that I am representing x2 by x1 corresponds to first natural frequency. 1 is representing corresponds to first. Now here if we will do calculation, it will come minus m, omega square is k by m plus 2k upon k. Now calculation is your part. M will get cancelled, minus k plus 2k is plus k divided by k, it is coming 1. Okay, I will explain. But similarly, if you want to calculate second mode shape, na, okay, what I am trying to say, for that calculate x2 by x1 corresponds to second natural frequency. For that we'll put omega by omega 2, in this case it is root 3k by m, means we'll replace omega square by 3k by m. Now you can do calculation. If you put this in equation 5, in this equation, you will get x2 by x1 corresponds to second natural frequency. Above side I am writing 2. This 2 is representing second natural frequency. Now after putting, you can do calculation. It will come minus 1. I am not going on calculation. Okay. So how I will write first? Actually, now first mode shape I will write like this. Okay. Actually, it represents like if suppose first is corresponds to x1, second is corresponds to x2. Just think, if x1 is 1, what will be x2? It will be also be 1. So this is first mode shape. Okay. Instead of that, you can also write like this, minus 1 minus 1. If x1 is minus 1, both are ultimately, na, see, second is representing x2, first is representing x1, but not their value. Actually, na, this ratio I am writing like this. It is representing x2 by x1. Since I calculated x2 by x1, na, that's why I am saying this divided by this. So if the ratio between them is 1, okay, here also ratio between them is minus 1. You can also write like this, 1 into 1 transpose. So whenever I will write, now I will write like this. If x1 is 1, what here will come? Okay, here. Sometimes it might be possible option is given like this. If here it is 1, what will become here? Or ultimately the ratio between them should be maintained this. Significance I will discuss, but like this we write first mode shape. How we write second mode shape? If x1 is 1, x2 will be minus 1. Instead of this, if you are writing like this also, okay, ultimately ratio between them should be minus 1. If you are writing like this, that is also correct. If you are writing like this, 2 minus 2, it is also correct. Minus 2, 2, that is also correct. But the ratio x2 divided by x1 should be minus 1. Yes or no? Now, what is the meaning? Now, it, as earlier I was saying, based on initial displacement, it will decide how vibration will occur. Either it will vibrate with only with omega 1 first natural frequency, or it will vibrate only with omega 2, that is second natural frequency, or it will vibrate with the combination of these two. So see now this is important. If initial displacement in both the masses which we are providing, if it is maintaining this, that is the ratio between x2 by x1 is 1. So its system will vibrate only with first natural frequency, whose that is with frequency omega 1. Means in the equation of x1 x2 only one simple harmonic term will come, whose frequency will be omega 1. But if initial displacement in both the masses is maintaining this ratio, means suppose x1 I am taking 1 centimeter this side, so x2 I should take minus 1, means this side 1 centimeter. Value same opposite direction as per this. So if it is maintaining second mode shape relation, okay, then it will vibrate only with frequency omega 2. Clear? And the initial displacement which I am providing in both the masses, neither following it is first mode shape relation, nor it is following second mode shape relation, then it will vibrate with the combination of frequency omega 1 and omega 2. That is first conclusion. Okay. But now calculating first second mode shape, if initial spring mass system diagram is given, is very lengthy process. So if question will come, either examiner will give this equation directly, or examiner will give some basic information through which question will become easy. Like if you see this question, in this question this diagram is given. See what I am trying to say. So examiner is asking first mode shape. It is given 1A transpose, means examiner is going, it is 1A. So what is the value of A? Now here now some data is written. Suppose if this data is not given in the question, then also you can solve this question. How? Find the frequency and corresponds to first natural frequency, calculate x2 by x1. Suppose x2 by x1 is coming 0.5. So can I say it will be like where it is x2 by x1 corresponds to first. So when x1 is 1, x2 will be 0.5. Okay. So in this case, A will be 0.5. I'm not saying this is the answer. Like this, you can do calculation. But here, that is very lengthy. So see, here some trick is given. That much of calculation is not required. What is the trick? See here now, already it is given. The initial displacement is in the both the masses is this. It is x1, it is x2 at t equal to 0. And examiner is saying system is already vibrating with first mode shape. So when system will vibrate with first mode shape, means vibrate with only first frequency, when the x2 and x1 is maintaining first mode shape relation. So can I say, since as per this initial displacement, examiner itself saying it is vibrating only with frequency omega 1. So here even calculation is not required. Can I say this initial displacement will maintain first mode shape relation? Means whatever x2 by x1 is coming as per this initial displacement, that will maintain first mode shape relation. Why, sir? Because examiner is saying it is vibrating with first mode shape. So right now, as per this data, can I say x2 by x1 is 1.24 divided by 2. And since it is corresponds to first mode shape, so it is nothing but it is representing x2 by x1 corresponds to first natural frequency. Okay. And how much it is coming? 1.24 divided by 2, that is 0.62. Okay, good. Now, if x1 is 1, how I can write first mode shape? So, x2 will be 0.62. Okay. Now, in examiner, it is given first mode shape is 1A. So, can I say A is coming 0.62? But with this data, I cannot calculate second mode shape because examiner is not saying it is displacement corresponds to second mode. Okay. Now, if suppose this data is not given, if proper calculation for this question to calculate first mode shape, now I am 100% sure corresponds to first natural frequency, it will come equal to this. This is known as aptitude. You should know how to apply your aptitude. That's why read the complete question. Okay. Like I will discuss this question also, but before this, I am discussing first this question. Why, sir? In this question, examiner is saying, this is first natural frequency, it is second natural frequency. This is first mode shape, this is second mode shape. It is MSQ, more than one option can be correct. Now, we are providing initial displacement with zero velocity. Then which one or more of the following option is your correct? So see, whatever initial displacement again, if it is maintaining this, it will vibrate with frequency omega 1, means this. First natural frequency, if it is maintaining this ratio, it will vibrate with frequency omega 2, that is second natural frequency. If it is neither maintaining this nor maintaining this, so it will vibrate with the combination of omega 1 and omega 2. Right now, as per first, see here, x2, calculate x2 by x1. x2 by x1 is minus 3.16 divided by 6.32. Yes or no? For option A. It is minus 4.496. And here x2 by x1 is minus 3.16. Here it is plus 3.16. So can I say here initial displacement is neither maintaining first mode shape nor maintaining second. So it will vibrate with the combination of omega 1 and omega 2. But this option is saying it is vibrate with only with second natural frequency. It is incorrect because it will vibrate with the combination. So A is incorrect. Okay. Now read option B. Here it is written initial displacement of x1 is 2. X2 is minus 6.32. So what is x2 by x1? Minus 6.32 divided by 2. It is minus 3.16. Here x2 by x1 is minus 3.16. Means here it is maintaining first mode shape. And since it is maintaining first mode shape, so it will vibrate only with first frequency. So it will vibrate only with first, and same is written here. That's why option B is correct. What about C? Initial displacement x1 2, x2 minus 2. So here minus 2 divided by 2, it is coming minus 1. Minus 1 neither maintaining this because it is ratio is minus 3.16 nor maintaining this because it is 3.16. So it will vibrate with combination of omega 1 and omega 2. And same is written here. See, it is saying it will vibrate with the combination of first and second frequency. So C is also correct. Yes. What about do? x1 is 1, x2 is 2, minus 6.32. So it is minus 6.32 divided by 1, minus 6.32. Not maintaining this because it is minus 3.16 ratio. Here it is 3.16 divided by 1, that is 3.16. So it is not maintaining both the ratio, both mode shape, means it will vibrate with the combination of omega 1 and omega 2. But here it is written it will vibrate only with first frequency. So that's why D is incorrect. Okay, this is good question. So for this question, the correct options are option B and C. Clear? Yes. Yes. Now, this is last question. After that, I will discuss some question related to infinite degree of freedom. Okay. See what this question is saying. The mode shape of an undamped 2 degree of freedom system are 1.5 transpose and 1. So when it is given like this, so it is representing first, it is representing second. Correspond natural frequency. It is first natural frequency, second natural frequency. It is in hertz. If you want, if required, you can convert that in radian per second also. Now, exam asking maximum amplitude of vibration of the first degree of freedom due to initial displacement of 2,1 transpose in mm and 0 initial velocity. Good, 0 initial velocity is given, na? But see, here this data is written. Is this corresponds to, even if this is not written, na? By looking this, you can tell. Vibration is occurring only corresponds to first degree of freedom. How? It will see x2 by x1. It is 1 divided by 2, that is 0.5. Okay. Now here x2 by x1, 0.5 divided by 1, 0.5. So it's actually initial displacement is maintaining first mode shape. Means here system is vibrating only with first frequency. That's it. Only with first frequency. Okay. Like if suppose this data is given like this. Okay, which is maintaining this, so it will vibrate only with second frequency. If data is given like this, it is neither maintaining this nor maintaining this, so it will vibrate with combination. Okay. Now before solving this, now how you can write the complete equation of x1 and x2? Right now I am writing the equation by assuming it is vibrating with the combination. If it is vibrating only with frequency omega 1, that is more easy. Okay. So suppose if system is vibrating with the combination of omega 1 and omega 2, so how you can write the equation of x1, which is the displacement of mass 1. See, first remember, but I am writing the equation by assuming it is vibrating with 0 initial velocity, because if a question is coming in which examiner is asking final equation of x1 and x2, na, generally it will come with 0 initial velocity. Means initial velocity of both the masses are 0. See, now remember, whenever initial masses are of initial velocity of both masses is 0, na, so see, actually in harmonic term we are writing sin omega t plus phi, na. So simply you can remember, whenever velocity is 0, initial velocity is 0, sorry, phi will always be pi by 2. For single degree of freedom also, one question I had discussed, whenever system is vibrating with 0 velocity, okay, phi will always be pi by 2. Now if phi is pi by 2, sin omega t plus phi. Now I am saying with for 0 velocity, initial velocity, phi is pi by 2. So it will be sin omega t plus pi by 2, and sin omega t plus pi by 2 is cos omega t. So whenever you are writing the whether it is equation of x1 and x2, na, if it is vibrating with 0 initial velocity in harmonic term, instead of sin omega t plus phi, you can directly take cos omega t. Okay, okay. See, only for single, if x is a sin omega t plus phi, so if phi is pi by 2, it will be a cos omega t. Now for this initial velocity is 0, because if x dot will be a sin omega t, a omega sin omega t. If it is cos omega 2, x dot will be a omega sin omega t. Now here if you put t equal to 0, sin 0, initial velocity is 0. So whenever initial velocity is 0, now in harmonic term directly use cos omega t. Cos omega t. Yes. So what will happen now? What will be the equation of x1? So see, when it is vibrating with first natural frequency, that is omega 1. So see, amplitude of mass 1 corresponds to first natural frequency is capital X11. It is not overall, it is the amplitude of mass 1 corresponds to first natural frequency. For mass 1, that's why capital X1 corresponds to first. Okay, now harmonic term. So harmonic term will be cos omega 1t. Why omega 1? Because it is corresponds to first natural frequency. Okay. And whenever initial velocity is 0, instead of sin omega t plus phi, directly you can write cos omega t. Means phi is pi by 2. Plus, if it is only vibrating corresponds to first natural frequency, it is completed. But if it is vibrating with combination, that's why I'm writing. Now, when it is vibrating with frequency omega 2, so amplitude of mass 1 corresponds to second natural frequency will be x12. top is representing corresponds to which frequency? And since it is amplitude of mass 1, suffix I am taking x1. It is the amplitude of mass 1 corresponds to second natural frequency. So here cos omega 2t term will come because it is corresponds to second natural frequency. Yes. Whenever now, if initial displacement is maintaining first mode shape, even if you will do calculation now, this term will automatically become 0. Okay. Yes. Similarly, x2. How we can write the equation of x2? So, see, the amplitude of mass 2 corresponds to first natural frequency. It will be x21 cos omega 1t because it is corresponds to first, plus amplitude of mass 2 corresponds to second natural frequency. It will be x22 cos omega 2t. So this is the final equation of x2. Similarly, here examiner asking now the maximum amplitude. So see, here this is initial displacement, which can I say x1 at t equal to 0 is 2 mm. First it will represent x1, and x2 at t equal to 0 is 1 mm. Okay. Even if this line is not written, you can see it is maintaining first mode shape relation. So here vibration will only occur with first natural frequency. Okay. Okay, means in equation of x1 and x2 only one harmonic term will come whose frequency is omega 1. Okay. But suppose even if you are not able to recall this, see, equation of x1, it will be capital X1 corresponds to first natural frequency cos omega 1t because it is corresponding to 0 initial velocity. Now, if you are 100% sure only vibration is occurring corresponds to first natural frequency, you need not to write second term. But suppose you are right, like here I don't require to write second term, but suppose if you are getting confused, then write second term also. It will be capital X1 corresponds to second cos omega 2t. After calculation you will come to know automatically it will come 0. Yes. Suppose this is equation 1. Now displacement of mass 2 x2, it will be capital X1 corresponds to first capital X2, amplitude of mass 2 corresponds to first cos omega 1t plus capital X2 corresponds to second cos omega 2t. Now what you can do now, right now can I say it is first mode shape 1.5, and first mode shape represent capital X2 by capital X1 corresponds to first natural frequency, which is 0.5 divided by 1, that is 0.5. So can I say x2 1 is 0.5 x1 1, yes or no? So here if you want you can replace x2 1 by, I am simplifying this, 0.5 x1 1 cos omega 1t. Similarly x2 2. This is second mode shape na. Now we know capital X2 by capital X1 corresponds to second natural frequency. It will be minus 0.6575 divided by 1, which it is minus 0.675. Here will use capital X22, it is minus 0.675 X12. So I can replace this X22 by minus 0.675 capital X12 cos omega 2t equation 2. So now you can see overall two unknown are coming, x11, x12. How we can calculate? So I know at t equal to 0, x1 is 2 mm. So in equation 1, put t equal to 0 and x1 equal to 2 mm. So equation 1 will become x1 equal to 2 mm and t equal to 0. So it is cos 0 is 1. So it is capital X11 plus put t equal to 0. It is capital X12. So this is equation 3. Similarly, now we know put t equal to 0. X2 is 1 mm. Okay. So put in the equation of x2. I am putting here x2 is 1 mm equal to t equal to 0. Cos 0 is 1. So it is 0.5 capital X11. It is minus 0.675 capital X12 cos 0, which is 1. It is equation 4. Now you have to solve equation 3 and 4. How will solve? What I am doing in equation 4, I am multiplying 2. So it will become 0.5 into 2 minus 1. Here it is plus 1. Coefficient of x11. And add them. So x11 part will get cancelled. You will get x12. So what I am doing? Equation 3 plus equation 4 into 2. I am doing this. So do this in LHS. It will become 2 plus 2 into 1. That is again 2. That is 4 equal to. It will be x11. 2 into 0.5 is 1. So minus x11. Already minus is coming. So that part will become 0. Now it will be equal to capital X12 Now twice of this, it is, sorry, it's my type. Sorry. See, if we'll put t equal to 0, x2 equal to 1 mm. So x2 equal to 1 mm. We'll put t equal to 0 now here. Cos 0 is 1, so it is plus 0.5 x11. This is typing error. Here cos 0 is 1, so it is minus 6.5 x12. Actually, it is plus. So now what we will do, in equation 4, I will multiply 2, so it will become 1 plus 1. Here also plus 1 is coming, so subtract that. Actually, we need to subtract. Here minus 1. So it will become, see, 2 minus 2 into 1, that is 2. That is equal to, it is x11, 2 into 0.5, 1. Subtracting, so it will get cancelled. Now it is equal to x12 minus, now it is minus 0.675 into 2, that is minus 1.35. This minus is already coming, minus 1.35 x12. But see, this is 0, so it is coming x12 1 plus 1.35, that is 2.35. But ultimately x12 is coming 0, but that I already know. Why, sir? Because it is corresponds to first mode shape, so definitely x12 will come 0. That I was already knowing, but I have proved also. Okay. Yes. Okay. Like if initial displacement is not maintaining first mode shape relation, na, so both x11 and x12 will come. Okay. But here x12 is coming 0. Now put the value of x12 either here, either here. Suppose if I put here, so from equation 3, 2 is equal to x11 plus x12, x12 is 0, so x11 is coming 2 mm. Okay. Now put this final values in equation 1 and 2, you will get the final equation of x1 and x2. So see, equation of x1 is coming capital x11, which is 2 mm cos omega 1t, other part is 0. x2 is coming, it is 0.5 x11, 0.5 x11, which is x11 is 2 na, cos omega 1 2, other part is 0, so it is coming 1 cos omega 1t. Okay. Yes, but you can easily derive this because already initial expression is maintaining first mode shape na. So when you are writing this, you can directly ignore this part. Why, sir? Because it is corresponds to first mode shape, means omega 2 term will not come, so only this will come, this will come. Now put t equal to 0, x1 equal to 2, you will directly get x11 equal to 2, so 2 cos omega 1 2. Put t equal to 0, x2 equal to 0, you will directly get x21 equal to 1. So automatically, so it will take less time. Okay. Now can I say the amplitude of mass 1 is 2 mm and amplitude of mass 2 is 1 mm. So which is overall max amplitude, it is 2 mm. So can I say for this question overall max, if exam asking amplitude of first mass, answer is 2 mm. Amplitude of second mass, answer is 1 mm. Overall max amplitude, answer is 2 mm. So in this question, examiner asking overall maximum amplitude, so directly answer will be 2 mm. Clear? Now some question I am discussing related to infinite degree of freedom na. Okay, this question I am discussing, but in this question I will make some summary. Like whenever it is the case of na, whether it is longitudinal vibration of bar, transverse vibration, torsional vibration of shaft, and transverse vibration is string, not beam. Beam case will come separate. In infinite degree of freedom na, all are analogous to each other, only some difference will come. And how you can remember na, whether it is longitudinal vibration of bar, torsional vibration of shaft, or transverse vibration of string, not beam of string. See here na, differential equation in infinite degree of system, partial differential equation comes, and it is like this. It is known as wave equation. It is like this: del square y by del x square is equal to 1 upon c square del square y by del t square. See, this equation is known as wave equation. Okay, if it is for, see, if it is torsional vibration of shaft na, so instead of y, theta will come, because angle of twist is theta na. So the difference is only for torsional vibration, it will be del square theta by del x square equal to 1 upon c square del square y by del t square. Okay. Okay. So for they are analogous na. For torsional vibration, for it is for longitudinal vibration of bar, it is for torsional vibration of shaft. Pattern is same, equation is same, but only instead of y I am writing theta, del square theta by del x square equal to 1 upon c square del square y by del t square. Okay, 3 is the constant. the formula to calculate C for the bar is, and what the formula to calculate C for the shaft is. Okay, so for bar the formula to calculate C is either root E by rho. E is the Young modulus of the bar and rho is mass density in kg per meter cube. Now rho is kg per meter cube. Instead of this, you can formula like this also. Root A is axial rigidity upon small m. Small m is nothing. It is mass per. Don't think it is total mass. It is mass per unit length. See, I will suggest remember only this because both are same. See, mass per unit length. Mass per unit means, see, total mass is rho al. So can I say mass per unit will be rho A? So if you replace m by rho A will get cancelled. You will get this. Now why I written like this now? Because here you can remember the equation of C like this. Like here E is axial rigidity. Here in torsion vibration it will be GJ, that is torsion rigidity. Divided by below side is coming I. But I is not total mass inertia. It is mass inertia of shaft per unit length. In continuous, this case is known as continuous vibration. Now, continuous vibration means whether it is bar or shaft, they are not massless. If they are having mass, so in that mass, infinite degree of freedom vibration occurs, which is known as continuous vibration. So this is C is constant. But here how we'll calculate frequency? That is very important. So see here, if you find the solution of y now, actually in solution y you will get the two function. One function belongs to variable x. Another function will belongs to variable t, because here two variable is coming now. But it will calculate now. It comes like this, like it comes a sine omega by cx plus b cos omega by cx. Now function of time a sine omega t. Sorry, c sine. Okay, here this c is not this c. It is constant. I am writing with capital letter. This c is this constant, but this c is A, B, C, D are arbitrary constant. Capital C sine omega t. I had discussed this infinite degree of freedom vibration in YouTube also. Now you can watch that lecture. Capital D cos omega t. Okay. And omega is the frequency of this system. And here I will get infinite value of omega. That's why it is having infinite degree of freedom. Now how will calculate this omega equation? Omega. For that now some initial condition is required. Okay. From that. But you need not to remember this. If you want, you can remember. But I will suggest at least remember this solution for, okay. Now, it is for torsional vibration only also. But here only difference is theta will come. Okay. Now, A, B, C, D are arbitrary constant. Now, we will discuss these things mainly for three boundary condition. Okay. First boundary condition I am taking as free. Or suppose first I am taking fixed. Now, I am not going derivation. Fixed na, see, miss, this is the boundary condition. It is for shaft also, but I am writing in terms of longitudinal vibration. Same will come for torsional vibration also. Instead of y, only theta will come. So this is fixed. Yes. Now here what will happen now? At x equal to 0, it is fixed connection. I am writing boundary condition. So at fixed connection now, always y will be 0. So can I say at x equal to 0, y equal to 0? Okay, at x equal to L also, okay, y is 0. So if you use this two boundary condition, you will get, after solving this, you will get an equation which is known as frequency equation. And here now for fixed connection, frequency equation comes in terms of sine. It is like sine omega L by C, remember this, equal to 0. For fixed connection, frequency equation comes like this, sine omega L by C 0. Now, when sine theta is 0, when theta is L by. So, here omega L by C, if you remember this, you can easily write this, it will be n pi. You can calculate value of omega also. And here n is starting from 1, 2, 3, 4. Okay. If you put n equal to 0, sine 0 is also 0. But here if you put n equal to 0, omega will come 0. If omega is coming 0 now, means this bar is vibrating like this. Means no deformation is occurring in the bar. But if both end are fixed now, bar cannot vibrate like this. That's why now, if at least one end of the bar is fixed, n equal to omega equal to 0 is not possible. That's why I'm saying n is starting from 1. Okay. Now, sometimes now, if examiner asks fundamental frequency. So, what is fundamental frequency? Now, I'm not writing here. The first non-zero frequency is known as fundamental. Here, if you put n equal to 1, it will come non-zero. So, that is known as fundamental frequency. It will be pi c by L. And what is c? For bar, it is root E by rho. Okay. That is different thing. So, that is known as fundamental frequency. Okay. If it is having second fixed free connection, means one end is fixed, other end is fixed. Boundary condition is like, suppose it is like this. From here I am taking x. So at x equal to 0, y is 0. But at x equal to 1, see, in bar, longitudinal vibration of bar, or in torso vibration of shaft, at free end, remember now, del y by del x differentiation of that variable with respect to x will be 0. How? I am not going on derivation. Just at fixed end, y is 0. At free end, for longitudinal and torso vibration of shaft, I am saying del y by del x will be 0. Like if it is shaft, del theta by del x will be 0. Now, by using this, you will find frequency equation. It will comes in terms of cos here. Cos omega L by C equal to 0. So, omega L, when cos theta is 0 now, when theta is 2n plus 1 into pi by 2. Remember that. This you have to remember. Now, here n is starting from 0. It doesn't mean if you will put n equal to 0, it is coming 0. No, it is not coming 0. So, actually 0 is not coming. Okay. Okay. So, here if exam asking fundamental frequency, put n equal to 1. Here exam asking fundamental frequency, just put n equal to 0. You will get first non-zero frequency. Okay. Third is free connection. Okay. Free means it is like this. So, here at x equal to 0, del y by del x is 0. At x equal to L also, del y by del x is 0. Now, for free connection, now frequency equation comes same as for fixed connection. Means here frequency equation is again sin omega L by C equal to 0. So, omega L by C will be n pi. But only difference is now, here 0 frequency is also possible. So, here n will start from 0, because if you put n equal to 0, 0 will come. Now, by putting n equal to 0, omega will come 0. That is only possible in free connection. So, when omega is 0, now that is known as rigid mode frequency. Rigid mode frequency, because here 0 is also possible. Rigid means bar will vibrate like this, but not without any deformation. But see, if examiner is asking first fundamental frequency, don't say answer is 0. First fundamental frequency means first non-zero frequency. So if I put n equal to 0, I am getting 0. So that is rigid mode frequency, not fundamental. Fundamental frequency, again I will get first non-zero. So by putting n equal to 0, it is coming 0. That is not answer. By putting n equal to 1, it is coming non-zero. So fundamental frequency is coming by putting n equal to 1. Remember that. Fundamental frequency means first non-zero frequency. If you want, you can write. Nah? Like now come to this question. It is saying boundary condition of rod under longitudinal vibration, means it is longitudinal vibration of bar. It changed from fixed to fixed free. Then fundamental natural frequency of the rod is now k times the original frequency. So see, what is k? So see, originally it was fixed. Okay. Okay, fixed. Suppose for this case, omega is fundamental frequency is omega f1. How will you calculate? For fixed frequency equation is terms of sine, means sin omega L by C equal to 0. So omega L by C will be equal to n pi, n is starting from 1. So first, okay, miss, can I say omega is n pi C upon L, and is starting from 1. So first non-zero frequency I will get by putting n equal to 1. So you will get omega f1 by putting n equal to 1, which is coming pi C by L. Good. This is original. Now later is fixed free. For fixed free, frequency equation is in terms of cos omega L by C is 0. So omega L by C will be equal to 2n plus 1 into pi by 2. Here n is starting from 0. Okay. Okay, if you calculate omega, it is coming 2n plus 1. Okay, into C pi by 12. Check the calculation. Na? So first fundamental frequency for case 2 will come. Put n equal to 0. It is coming 1 by 2, means non-zero. So non-zero means that is fundamental frequency. So it is coming pi C by 12. Check. Okay. So now examiner is saying omega f2 by omega f1 is k. So what is the value of k? Okay. So omega f2 is pi C by 12. Omega f1 is pi C by L. So pi C by L is common part. Na? So a common part will get cancelled. So apart from pi C by L in omega f2, it is coming 1 by 2. Divided by omega f1. In omega f1, apart from pi C by L, only 1 is coming. So it is 1. Calculation is your partner. I am not explaining the calculation. So k is coming 1 by 2. You can check. So for this question, k is 1 by 2. Matching with which option? Option A. Clear? Now this question is for torsional vibration, but again you can see it is changed from fixed free to fixed fixed. So examiner asking the value of K. So this I am giving homework because it is similar type of question. Now this is related to boundary condition. It is the equation of for torsional vibration. You will see na, it is satisfying my condition because I was saying that equation is like this: del square theta by del x square equal to 1 upon c square del square theta by del t square, and c is what is c? C is root gj by I naught or gj by I. So if you replace c by root gj by I na, so c square will be gj by I, so it is gj by I. So with del square theta by del t square, above side I is coming, yes, and gj if you set this side with del square theta by del x square, gj is coming. So same is there, no difference equation is. Now examiner saying shaft is fixed at both ends, so what will be boundary condition? At fixed and theta is 0. So can I say at x equal to 0 also theta 0, at x equal to L also theta 0, matching with option B. If examiner is saying shaft is free at both ends, so this will be the answer. Okay, but right now both end fixed, so that's why option B is correct. Now actually now this is linked question. Okay, now second is question is saying again, if the actually now these two questions are linked question because earlier in GATE now linked question was coming. So actually this data is for other question also. They are linked question. So here also now it is mentioned that shaft is fixed at both ends because they are linked question at both. So it is fixed connection. Exam asking frequency of nth mode. So for fixed, we know frequency equation is sin omega L by C, which is equal to 0. Yes. So omega L by C will be equal to n pi. So can I say omega will be n pi C by L? This is nth mode frequency. But option is given in terms of J, Gj like this na, n pi C upon L. Now what is C? C is root Gj by I. So just replace C by n pi by L root J. They are linked question na, means again connection is fixed. So C is root Gj by I. So actually omega is for nth mode is n pi by L root Gj by L. For fixed connection, omega L by C is 0. Means omega L by C is n pi. Means omega is n pi C by L, and C is root Gj by I. That's just I done that replacement. Now, the number of natural frequency for a beam, cantilever beam, if it is given like this, means we are considering the mass of beam. If we are considering the mass of beam, degree of freedom will be infinite. So natural number of natural frequency is also infinite. Yes. Now this is last question. So now this is the question, just 5 minutes. This is the question related to transverse vibration of beam. Now in transverse vibration of beam is na little bit complicated. Here now if question will come na, generally question will come only related to boundary condition. See, now I am discussing in summary transverse vibration of beams. Here na, like it is a cantilever beam, mass is given, here vibration is occurring, but it can be cantilever beam also, it can be simply supported beam also, it can be overhanging beam also, it can be fixed beam also, but that is little bit lengthy. For this case, that partial differential equation comes in the order of fourth. Okay, it is del to the power 4 y by del x to the power 4 plus 1 upon c square del square y by del t square, that is equal to 0. If you want, you can remember this, but not necessary. And here if we calculate c na, it is root ei by m, like in torsion it was gj by I, it is ei by m, but m is not total mass, it is mass per unit length. Okay, so here what will happen na, if we solve this na, see, it will be the function of x and function of time, but in function of x na 4 arbitrary constant will come because power is 4. In function of t, 2 arbitrary constant comes. So actually its solution is like this. It is very complicated. A sin beta x plus b cos beta x plus c sin hyperbolic beta x plus d cos hyperbolic beta x. into function of time, ABCD I used. So E sin omega t plus F cos omega t, and inside the time function, the coefficient of time is omega. So what is omega again? It is the natural frequency of this system. What is omega again? It is the natural frequency of this system. And what is C? C is root EI by, what is C? C is root EI by M. And here beta is now, you can remember like this, beta to the power 4 is omega square by C square. But this is very complicated. So no, very rare question will come from this, but question if it is coming, it can come corresponds to boundary condition. Okay. And from corresponds to boundary condition, how you can remember now? Here, generally you will find 4 type of end condition. One is, it is fixed. So you can remember here now, actually at fixed condition, the end, neither it will translate in one direction nor it will rotate. Because in beam I am discussing, means I am talking with respect to transverse load. So in transverse load, 2 things can occur. It can deflect like this and it can have angle of slope. But at fixed end, we know both vertical deflection and slope will be 0, and deflection is 0, means at fixed end y will be 0. This you are using in beam in strength of material also. And at fixed end, del y by del x will also be 0 because slope of deflection curve is 0. This is the boundary condition related to fixed end. Second, sometimes support will come which is hinge or roller support. Okay. Now see, at hinge, whether it is hinge or with respect to transverse load, both we have a same. So at hinge and roller support, vertical deflection will be 0, means whether it is hinge or roller, y will be 0. But del y by del x will not be 0 because slope can come. But I require from one is and condition, I require 2 boundary condition. So see what I am trying to say. If it is hinge support now, so here force reaction can come, but here no moment reaction will come. So if force reaction is coming now, means shear force can come at this end. But can I say at this end bending moment will always be 0? Because if I will calculate bending moment of this section by taking left portion, it will be 0. Shear force will come due to this concentrated force. So at hinge support now, bending moment is 0. Now whenever bending moment is 0 at any end, remember del square y by del x square will be 0. If shear force is 0, right, or shear force is not 0, then del cube y by del x cube will be 0. What I am saying, if bending moment is 0, del square y by del x square will be 0. Why, sir? Try to recall, EI d square y by dx square is equal to mx. If mx is 0, means d square y by dx square equal to 0. And slope of mx means dmx by dx is shear force. Now, if I will differentiate EI d square y by dx square one more time with respect to x, it will be EI d cube y by dx cube, which is dmx by dx, which is shear force. So what I am saying, if shear force is 0, means d cube y by dx cube will be 0. If bending moment is 0, means square will be 0. So see, at hinge or roller support now, shear force can come because force reaction can come, but bending moment will be 0. And bending moment is 0, means here del square y by del x square will be 0, whether it is hinge or roller. Now next is free end. At free end, I am talking about free end. So see, at free end neither y is 0 nor slope is 0. But at free end, no force reaction, no moment reaction. No moment reaction means bending moment is 0, means del square y by del x square at free end is 0. Okay. No force reaction means shear force is 0, means del cube y by del x cube is 0. Like here I require for each beam 4 boundary conditions. Sometimes examiner can ask bending. Suppose this is a cantilever beam, x I am taking from here, this is L. So see, at x equal to 0, you can see it is fixed. And at fixed second, deflection and slope is 0, means y is 0 and del y by del x is 0. Now at x equal to L, it is free, and at free end, since no force reaction, first take no moment reaction, means del square y by del x square 0. No force reaction, means del cube y by del x cube 0. So sometimes examiner can ask only this boundary condition. Most of the time question will come related to boundary condition. I am writing only for one more case. Suppose it is simply supported beam like this. X I am taking here. This is L. So at x equal to 0, it is hinge. Hinge or roller support behave same. At hinge support, vertical deflection is 0, means y is 0. Slope is not 0. But here is about force reaction comes means shear force can come, but no moment reaction means bendment is 0. Bendment is 0 means del square y by del x square is 0. Same conclusion is coming for x equal to L also. Why? X equal to it is roller support. Means vertical deflection is 0. Okay, no slope 0. Force reaction can come, but shear force is not 0, but moment reaction is 0. That's why bendment is 0. So del square y by del x square equal to 0. Yes. Okay. Sometime na this type of question can come. Okay. Like it is the equation here, instead of y, examiner is writing is w. Y is deflection, here w is the transverse direction deflection. Okay. Now here implicit it is rho, ultimately na it is following that relation. C is root EI by m. M is mass per unit length, which is will be equal to rho into A, because mass is rho AL. So mass per unit length is rho AA. So in C formula, if you replace m by rho A na, and if you put and simplify this, automatically this equation will come. So don't worry about this. Okay. Now examiner is saying it is simply supported beam, but assume, because here calculation is tough, so examiner is saying assume the mode shape in fundamental mode is to be sin pi x by L. Then what will be the natural frequency of this system? So see, means what examiner is saying na, in the equation of x, the term which is coming as a function of x, in that term now only sin pi x by L term is coming, other term is not coming. Now if you try to recall, in the equation of x, sin beta x, cos beta x, sin hyperbolic x, cos hyperbolic beta x was coming. So try to take sin beta x term, because other part is not coming. So if I will equate this with sin beta x, so can I say beta is pi by L? If we will equate this with sin beta x, beta is pi by L. So this is beta. Okay. Now we know beta to the power 4 is omega square by c square. Okay. Means can I say beta square is omega by c? So square this. Beta square is pi square by L square, and beta square is omega by c. So omega by c is pi square by L square. So can I say omega is pi square c upon L square? Now what is the formula to calculate c? We know c is root EI by m, and m is mass per unit length, which is rho A. Not total mass, next it is rho A. So this is the answer. So this is first fundamental frequency, pi square by L square. Now in option L square is inside root, so it will be like this, pi square EI upon rho A L to the power 4, because if we are bringing inside root, it will be L to the 4 na. So it is pi square root pi square separately root EI upon rho L to the power 4, matching with which option? Option B. So this is correct answer for this question. Clear? Okay. So we have discussed the PYQs of vibration in GATE Aerospace. Okay, and I think it should be clear to everyone. Okay, so ending the class na. Hopeful this discussion is helpful for you, I'm hoping. Okay, and if you are having some weak topic or weak area na, you can watch my vibration lecture series which I had taken in this YouTube channel. So you